right, so table of content here. If you could push that button once. It looks pretty, it's a 2-pager, folks. Can you handle that? It was only 1 page yesterday, I think. So we'll work our way down through this theme of categorical variables. It will be mostly, if not totally, observed categorical variables. But when we get to topic 5 and 6, which will happen a year from now, we will talk about categorical latent variables as well, the mixture stuff. So today will be a day where we will take our time and build up a base for modeling components that we will use in later topics, including those a year from now. So it's going to be a little bit painful here and there for those of you who particularly have not taken a categorical data analysis course. It'll be a little bit painful, perhaps. It'll be new thinking, but force yourself to do it, you know? Like John F. Kennedy said, we do these things because they are hard, not because they're easy. And these are going to be hard things. Actually, I have the Boston accent version of that, but Linda says it's too much Swedish accent. You know, he gave that speech about people landing on the moon, when we landed on the moon. So categorical variable modeling is just about like difficulty level of landing on the moon. By the way, have you noticed that Linda has only a very slight Swedish accent? Her English is very good, actually. Maybe because she is actually an LA native. But enough about us. So here is the background that you don't want to hear about again. And this picture doesn't even move. So let's start here. Slide 12. So we're going to focus on categorical observed variables. And in the morning, we're going to talk about only observed variables, particularly regression analysis. And if you look at the second bullet, however, it will quickly get more intriguing, and we're going to bring in continuous latent variables in combination with categorical observed variables. The third bullet has to do with what we'll talk about in topics 5 and 6, so we're not going to cover that today. Although having said that, I actually will entice you with a precursor, first little sample of categorical latent variables in the context of regression with a count dependent variable and the so-called ZIP model. You'll get a lot of new acronyms now to use in your conversations. ZIP standing for Zero-inflated Poisson. So let's start with a simple example here. And many of our illustrations come from the field of alcohol research, largely because both the Mplus development and my own grants at UCLA were sponsored by the Alcohol Institute and our AAA. So for instance, if you take a look at, just to get our bearings here, 2 simple examples. Let's say that we focus on alcohol dependence and gender in the National Longitudinal Survey or Study of Youth, I think it is, where NRAAA added a alcohol supplement, extra questions related to alcohol use and abuse and dependence. You have a table like this, and the first thing you want to do is to figure out what it means, what are the variables involved. And we have apparently a gender here, female, male, as 2 separate rows. And we have alcohol dependence or not, as classified by diagnostic criteria, the DSM-3 perhaps at that point. Diagnostic criteria built up by symptom items in a survey. And we classify people as dependent or not dependent. So what we have is a 2-by-2 table. We have a two dichotomous variables, or sometimes we'll refer to them as binary equivalent. And we want to look at the relationships between those 2 variables. In some analysis, we're going to look at the variables in a symmetric fashion and just look at association between them. Sometimes, and mostly today, we're going to look at them in an asymmetric fashion. That is, we think of female or a male, the gender variable, as being a predictor or a covariate of alcohol dependence being in the dependent variable. So we have a total sample of 9176, and here's the gender distribution, 4573, 4603. And we count how many of those 4573 females are dependent and of those males who are dependent. And we calculate the proportion, 256 divided by 4573, same for males. And then we're going to introduce a quantity that we call odds. And that's going to be central, particularly in the context of logistic regression. So we are going to calculate odds as the ratio of the proportion divided by 1 minus the proportion. Proportion is the sample quantity, and it's then therefore an estimate of the probability of being alcohol dependent. So you can think of the odds as the sample quantity of the ratio of probabilities of being alcohol dependent versus not being alcohol dependent. So the odds is fairly low for female, a little bit higher or considerably higher for males. And if you take the ratio of the two odds, you have an odds ratio, as it says below the table, 0.179 divided by 0.059 is 3.019. And so that can be given, excuse me, a very simple explanation then, or expression or interpretation in words. Example wording, males are 3 times more likely than females to be alcohol dependent. Excuse me. And that's a very simple statement. The only problem is it's incorrect. And I just noticed that it's not that males are 3 times more likely, right? It's that the odds is 3 times higher. The odds is 3 times higher for males and females. Males being 3 times more likely would say that the probability is 3 times higher for males than for females. That's approximately true, but I think you should say here, males have a 3 times as high of an odds than females for being alcohol dependent. Males have a 3 times higher odds than females to be alcohol dependent. I think that's a more correct statement. Now, if you look at the bottom table here, and let's do it on here. Here it's a little bit of a different situation. Here we actually have a randomized trial. We randomize people into placebo or treatment. In this case, treatment is vitamin C against colds. So we know how many people are in each category here. We tried to have an even split, and we lost 1 person apparently, 140 and 139. That's a different sampling scheme than up at the top. At the top, we just take a random sample. Actually, we take a complex survey sample with stratification and clustering. But essentially, both gender and dependence distributions are unknown to us. It's a random variable how many people we're going to have here for the females and for the males. Whereas in the bottom part, we have fixed numbers down there. So we have somewhat different sampling schemes. And that gives rise to different names for the sampling distributions in statistics. Let me get back to that in a second. And I'll show slide 15 on both sides here in case the podium blocks your view. It can't be moved, so I can't do anything about that. Let's just refresh our memory from categorical data analysis about different kinds of probability concepts. So we have joint probabilities, we have marginal probabilities, and we have conditional probabilities. And you want to be able to tell the difference between them. Let's do this in the context of the example. U is, in Mplus notation, a categorical dependent variable. So in this case, it is the dependent, not dependent variable of the alcohol example. X is the male-female distinction for the gender variable. So U is alcohol dependence and X is gender. When we talk about the joint distribution, we're talking about the 2 by 2 table here. with, in this case, sample proportions, and they add up to 1.0, except rounding error adds up to 1.01, I think. But we're talking about these 4 cells in the 2x2 table. And if you think about these as probabilities, they're actually the sample counterparts. They are the probabilities in the joint distribution of these 2 variables. Now we can talk about the marginal distribution as well. Marginal distribution for U would be that only 11% are alcohol dependent, 90%, should add up to 1 as well, with given rounding, it doesn't. 90% not dependent. That's a marginal probability. And then finally, conditional probability is out here. For each gender, we ask, what's the probability of the person being alcohol dependent? So for females, it's the 6%, and for males, it's 15%. And those values, by the way, are the same as we see here, 6% and 15%, if you talk about the sample quantities. So what we have on slide 14, proportions, is the same as what we have in the marginal in the margins up to the right for slide 15. Conditional probabilities. Conditional probabilities is sort of conditioning on which row you're in, what's the probability that you are in, say, the dependence category. So we'll make that distinction, and we'll also make a distinction between different distributions. If you want to be fancy, a dichotomous variable can be called the Bernoulli distributed variable, and expectation of that variable, expectation meaning the mean in the population, is pi, probability of being in say, observing category 1, typically. Binomial is a sum of Bernoulli variable, or you can look at a proportion, and the expectation of the proportion is pi. So the observed proportion is a probability estimate. The variance is that pi times 1 minus pi divided by n expression. If you look at a table, if you look at a joint probability table like this, the standard distribution for that is a multinomial distribution, multinomial. That's sort of the counterpart to the normal distribution for continuous variables. It's one of these very often used distributions that's good to use for categorical variables. And the number of parameters is the number of cells minus 1. So you have 4 cells, so that we have 3 parameters, which are the parameters being the probabilities in the 2x2 table. Since the probabilities have to add up to 1, you only have 3 independent, mathematically independent probability parameters. And the multinomial, the maximum likelihood estimation of the probabilities in the table, those estimates are very easily obtained because they're simply the sample proportions. So what's intuitive is actually exactly the maximum likelihood estimate as well. That's not always the case in other settings for other distributions like continuous normal. And I was saying independent, well, I was talking about this case of Coles and vitamin here. That's actually if you think about yesterday, that's a multiple group setting, multiple group. You have 2 groups, treatment control. And the sampling then is often called an independent multinomial or product multinomial distribution, because the sampling is independently done in this group and from the group, in this group and in that group, independent observations. Now, very often these kinds of frequency tables, often also called contingency tables, the distribution for them is said to be Poisson, as you see at the bottom of the screens, Poisson. And that is then an alternative way to describe a distribution of a frequency table, alternative to the multinomial. You often see that used in context of so-called log linear modeling. Log linear modeling being an analysis of many categorical variables, looking at associations between variables, pretty much like a correlation matrix analysis for continuous variables. So you look at do two variables interact the same way for different levels of a third variable. You can have two-way or three-way interactions. So log linear modeling is a very nice technique that you should learn if you deal with a lot of categorical variables. And log linear modeling is actually possible in Mplus in a very powerful way, where you can also handle tables that have missing data, and actually tables where the variables are not perfectly measured, where the categorical variables have measurement error. So in fact, Mplus does the log linear modeling on the latent level, latent categorical variables. And there's an example of that in the Mplus User's Guide. Now, going further then, slide 16. And tell me if I'm going too fast or too slow.
I think you're fine.
Okay. Here's something that you should know about. In epidemiology, and I'm impressed that I could say that early in the morning. In epi, you talk about not odds ratios all the time, but sometimes you call it cross-product ratio. Here you have the same table that we looked at before. X is gender, U is alcohol dependence or not. And in the cells, we have now the probabilities. So we're looking at population concepts with the subscripts denoting which cell they're in. And in epidemiology, you often look at the relationship between U and X expressed as a cross-product ratio. And that is cross-product is because it's that top left quantity, probability, multiplied by the bottom right, divided by top right, multiplied by bottom left. So zip, you have like an X here going on. That's what this expression on the second line here says. But that kind of cross product is not intuitively interpretable. Instead, you rewrite it by simple algebra as the probability of U equals 1 divided by probability U equals 0 for X equals 1. So in the bottom row, divided by the same quantity for X equals 0. So you look at the odds of alcohol dependence for females, or for males rather, divided by the odds for alcohol dependence for females. So looking at it this way, after the equality sign is more intuitive, but it's the same algebraically as the cross product. And here it's just written out in probabilities. I'm trying to describe in words where I'm pointing because we're filming recording the slides, but there are slides on the computer, not slides from the screen. So we have tests of this log of this. This is a log odds ratio that we're talking about here, and we have tests for the log odds ratio. Instead of having the odds ratio, statisticians like to take logarithm, because it is often then a better approximation to a normal distribution, and we know how to test normal distribution using our approximate z test. You can also test proportions here to study the association between the variables. And we can do a Pearson chi-square or a likelihood ratio chi-square. The Pearson chi-square is perhaps more similar to the wall test, whereas the likelihood ratio chi-square is the likelihood-based test that we talked about, the log likelihood difference test that we talked about. And it's interesting, this is the Pearson chi-square is the familiar test of independence between these two variables. Now, this is just quickly trying to bring you up to speed here. And if you think that all of this seems extremely unfamiliar, well, then we have these references that I emailed some of you, most of you. You have the classic Agresti book, which is nice. Somewhat more statistically oriented than the Agresti Light book, Introduction to Data Analysis. It's also good. You have the Applied Logistic Regression book here by Hosmer and Lemeshow. And a very good book by Scott Long, which is in the Sage series, but not the green series, but the white series, which is thicker. And Scott has written a book that is very comprehensive statistically, but also he has a good knack for choosing words to guide you through the thinking of the models, so it actually suits non-statisticians as well. So that's a very good reference book. Now, what we're going to do here, Linda and I, is talk our way through a series of models where the dependent variable is categorical. And you know, it's all about what the dependent variable is. The dependent variable character decides what kind of statistical model you want to use. It doesn't matter what the independent variables are. It doesn't matter what the covariates are. As Linda said yesterday, they can be continuous, they can be categorical. If they have more than two categories, the categorical variable gets broken up into a series of binary variables, but they're all treated as, essentially treated then as continuous variables. That is, the values of the variable is what matters. But we're going to talk about models for the dependent variable, and we're going to say that we are going to move away from predicting a value, like y equals 10 or something like that, but instead, we're going to predict a probability. Our model is going to talk about probabilities for observing a certain category. So we're going to talk about dichotomous outcome variables, and we're going to talk about adjusted log odds, and we're going to go from the dichotomous to the polytomous multi-category case. First of all, talking about the ordered case. So this is an ordinal variable here in the third bullet, ordinal variable. And then we're going to talk about a nominal variable, the unordered case, or unordered polytomous case, a nominal response variable, like bus, train, car, bike. And then we're going to talk about multivariate categorical outcomes. So we're going to go through this. We're going to spend most of the time on the dichotomous outcome. We are, however, going to talk about the polytomous case and in terms of the ordered and unordered situation, because we are going to be particularly leaning on our knowledge in the unordered polytomous outcome case, the nominal case, when we come to topics 5 and 6. So latent class analysis, we're going to need this fourth bullet knowledge and use that. It's not going to be hard, but it just takes a little bit getting used to the different thinking in those areas. So what you learned today will serve you well up until the time that we get to, hopefully, to topic 8 in 2011, March. All right, so let me say a few more words about technicalities, and then Linda gets to have all the fun with the applications. Somebody is very active this morning. Beeping. All right, so we have lots of different kinds of logs that we want to understand. We have top left here on slide 19, a logarithmic function on the y-axis, which is a function of the x values on the x-axis. Why is this important? Well, first of all, the notation, E log, that's, logs can be computed with different bases, E being the natural log, E being 3.14, right? Something like that. 2.7? Yeah. Has it gone down? Yeah. That's inflation. 2.7, they say these. Okay. And then you have a base of 10 as well. So where do we use the logarithmic function? Well, we use it in the maximum likelihood estimation. Maximum likelihood maximizes the log of the likelihood. Statisticians, again, like to take logs because things become simpler. Things become more normal when you take a log very often. Products become sums. Sums are easier to handle than products. And what we are going to see is that this x then is a parameter, say one parameter that can vary rather. And we're saying that we want a high value of the logarithm, so a maximum likelihood value that is high. Very often we're going to operate in the negative down here. and then a negative of, say, minus 100 is better than minus 500. So have that picture in your mind. Minus 100 is a better likelihood, a higher likelihood than minus 500. Anyway, and log of 1 is 0. That's one thing. A totally different thing is the logistic distribution function. Distribution function is something that varies between 0 and 1. 0 and 1, and it describes the probability of having a value of x at least that high, so that much and lower. And it's the y-axis scale is therefore a probability between 0 and 1. So in this case, this x value corresponds to probability of being at x or lower of, what should we say, 0.8. And we're going to use that kind of distribution function to describe the probability that u is equal to 1. And we're going to talk about that in more detail. We're also going to talk about a logit and see how a curve like this can be straightened out into a line, lines being more easily interpretable to most people than curves. And we're going to see also that there's a connection between the distribution function and a density. Density in the, this is the population quantity concept. In the sample, it corresponds to the frequency distribution. So this is there's actually a logistic density. It looks like a normal, but it's slightly different, a little bit different tails. And the density then, this density corresponds to this distribution function. Actually, in mathematical statistics, you say that you take the derivative of the distribution function to get to the density. Now, here then, slide 20, you have logistic regression. It actually then uses the distribution function, which is described by capital F here, as a way to describe a regression on x. So we're going to relate u to x by a model that looks like top right. 1 over 1 plus e, 2.14 you say, to the power of minus beta 0 plus beta 1x. And it is then a non-linear function. So you can sit and choose different values of beta 0 and beta 1 and x and see how those values represent this curved line, this S-shaped curve. Beta 0 is the intercept because it doesn't multiply x, and beta 1 is the slope, okay? And it describes a probability. So that's our dependent variable, the probability of observing u equals 1. And therefore, probability of observing u equals 0 is, of course, 1 minus the probability of u equals 1, right? We're going to talk about that several times. So in that case, the logistic distribution function is giving the probability value u equals 1 on the y-axis for a certain x-axis value. And it can be portrayed as the area under the density to the left of this point. The area under the curve to the left of that point, beta 0 plus beta 1x, is the height of the distribution function. So this, you can put a little brace here on the left for the logistic distribution function, and the height of that represents the shaded area under the curve. So being in the category, in the section of the density that's to the left. At the bottom, you have the logistic density as the derivative of the distribution function, and it comes out to be a logistic density. And here you have an interesting pi squared divided by 3 component that will come in and haunt us for the rest of our days here. Pi in this case is 3.14. There is the pi, 3.14. And it's not the probability. And if you square that and divide by 3, that happens to be the variance of the logistic density. And the fact that that is not 1, as you know, often standardized variables are, is why probit and logit are different. So the difference between probit and logit, which we're going to talk about shortly, stems from this pi squared over 3. Now, probit regression is very much like logistic regression. Actually, let me have the logistic up here. So it's the same, except we change distribution function. On the left, slide 20, you have the logistic distribution function. On the right, you have the normal distribution function. They look pretty much the same, right? And so do the densities. So bottom right here, slide 21, you have a normal distribution. But they give somewhat different values. But the same idea holds. So if you look at formula 60, top right here, the probabilities then is described by not f but phi or phi, depending on where you come from, a normal distribution function. And yeah, that's all we have to say at this point. So if you go into the way you calculate phi, you have to go into your Stat 101 books, and the argument here, what sits in parentheses is called the argument, is the value in the outside of the table, and inside the table, I mean the margin of the table, and inside the table you get the probability. That's all I'm going to say there. Then you have, okay, you twisted my arm. Let's talk about this too. So you could talk about a, let me just say this. We'll hear this several times, but let me say it one more time. Let me say it first here again. Now, what's in parentheses here and what's in parentheses there, this is called the logit. That's a linear part. That's the linear representation corresponding to the line bottom left on slide 19. It's called a logit, the argument. If you are in probit regression, that argument is called a probit. And the probit, the logit is very easy to calculate. The probit is, you have to go backwards into the table. You have to go inside of the table and look first at the probability inside of the table to go out to the argument value in the margin of the table. And if you didn't understand what I just said, you can live happily ever after despite that. But now when it comes to these analyses, you can really have different level of ambitions for levels of ambition to penetrate the results. So very often I'm lazy and I just look at regression coefficients. And when I say regression coefficients, I mean regression slopes, beta 1 as we called it. There's signs and significance only. Is it positive or negative? Is it significant? Does that x variable have a significant effect on the dependent variable? But very often in applied work, you see reference to odds and odds ratios as explications of the results. And we're going to talk about that. That's one higher level of ambition. And down-to-earth interpretations also tie the results back to the probabilities for the outcomes as a function of x, which after all is how you started formulating the model in the first place. Now this looks like a scary slide, 23, but you can penetrate that by high school algebra knowledge. Let's just look at it since it's going to come back so many times. Early on we said that an odds for an event, alcohol dependence, as a function of x, is the probability that it happens versus the probability that it doesn't happen. So it's a ratio here. Probability that it happens, alcohol dependent, versus not alcohol dependent. That's an odds. If you're betting and go to Las Vegas, you know about odds. If you assume the model, of the logistic function, so that's one model, and the normal probit function is another model. But if you assume the logistic function, which is expressed here, it will give you a odds, or actually a log of the odds, that's linear in x. And when it's linear in x, it means it's easily interpretable. So linear in x at the bottom of slide 23 is that argument, beta 0 plus beta 1x. That is the log odds, which is the same as the logit. So if you go back up here, if you assume the logistic function, the logit, which is the log of the odds, where the odds is the probability ratio, and you stick in the probabilities according to the logistic function here inside of these big brackets, and you do a little algebra here, and a little magic happens in this step, and then the log of e to the power becomes the argument there. So the logit is the log odds, and the logit is linear in x. So those are the lines again. And therefore, that gives an interpretation for beta 1 in terms of log odds. After this, yeah.
Okay.
So, yeah, warm up. So if you look at screen slide 24, top there, we've summarized what we have at the bottom of slide 23. Logit equals beta 0 plus beta 1x. So you can think of the logit, or the log odds, same thing, as a dependent variable. Instead of u, you translate it into the log odds. Instead of probability u equals 1, you translate it into the log odds for u equals 1. And then it's a linear regression, which is much easier to work with or think about. So we say that when x changes 1 unit, it's the logit that changes beta 1 units. So this is in line with linear regression. When x changes 1 unit, y changes beta 1 units. But here it's the logit that changes beta 1 units. And if you don't like log of odds, if logs are hard to interpret perhaps, although statistically well behaved, they're harder to interpret, then you want to get to the odds. So to get rid of the log, you take e to the power of the quantity, and therefore e to the power of beta 1 talks about how the odds changes instead of the log odds. So in Mplus, you will see beta 1 estimates, and you will see e to the power of beta 1 estimates as well. And with that much statistical background, the hard part, Linda will come in and entertain you with some examples.
Okay. All right, so now let's get away from all those formulas for a few minutes and talk about some examples, like Bank said. So, wait a minute, what have you done?
Previous slide.
No. Okay, hold on. We'll get this 25. And let's have 26 over here. Okay. So first of all, let's take a look at some British coal miner data where the dependent variable was, have you experienced breathlessness? So that's our variable we've been calling u. And you could answer yes or no. So it's a dichotomous dependent variable. And if we look at the picture here, you can see that on the x-axis we have age. And on the y-axis, the proportion of people who said yes to the question about breathlessness. The red squares represent data points for different ages and the proportion of people in that age group that said yes. So this is our data. And the solid line, that represents doing a regular linear regression on this data as the linear regression we discussed yesterday. And so if we do a linear regression and we treat the variable breathlessness as though it were continuous and not binary, this is the regression line that we get. And you can see that here the regression line underestimates the data. Here it overestimates the data, and once again it underestimates it in this portion. So that treating this variable as a continuous variable does not fit the data very well. Now we can instead turn each of these regression points into a logit. And the way that we do that is we take the log of the proportion divided by 1 minus the proportion. So for each of these data points, we take the log of the proportion on this axis here, on the y-axis, divided by 1 minus the proportion, And then we get these logits. So the red squares represent logits. And then if we do a linear regression in the logits, we see that that the line fits the logits much, much better. So we can say that they're linear in the logits. So this relationship is linear in the logits. And that's the approach that we can take to doing logistic regression. And then you can then go back from the logits to probabilities or to log odds. So, but you create a linear relationship to make estimation easier. And then you can interpret it either the logits themselves, like Bengt just said, or you can create odds ratios, or you can create probabilities and look at those, depending on how you want to interpret the data. So the point is that the linear relationship is easier to work with. So now let's take a look at the data. And here we have the age variable x. So we have various groups, 22, 27, 32. We have the n, so that's a categorical variable also, but it doesn't matter the scale of that variable. We're treating it as continuous here. It's ordered. Then we have the total n in the sample. So for people in this age 22 category, there's 1,952, and 16 of them said yes to the question, have you experienced breathlessness? Now in the 27 age category, we have 1,791, and 32 said that they have experienced breathlessness. And if you just take a look, you can see that there seems to be an increase in people who experience breathlessness over time, except down here at 62. And we can turn this value, yes, into a proportion by dividing 16 by 1952. So then this column shows the proportion of people who have said yes to the question, have you experienced breathlessness? Now, in the last three columns, we give the results of analyzing the data using ordinary least squares linear regression, logit regression, or probit regression. So we've analyzed the data in three different ways. As you can see, and the ordinary least squares regression is represented by the line on the right screen. And you can see that I mentioned we have underestimated these first two. And not only have we underestimated, they have negative values. And a probability, can't take on a negative value. It goes from 0 to 1. And if you compare to the proportion, yes, is the sample data. And if you compare, you would expect the estimated model to be very close to that. And you can see that as this line doesn't fit the data, you can see that in the linear regression results. Now, in the logistic regression results, things look somewhat better if you compare proportion yes and logit estimated probabilities. But when you move to the probit regression, you can see that the results are even closer. And if you take a look at test of model fit, the logit model has a higher chi-square value than the probit model. So the probit model actually does fit better. And as we go forward looking at some other examples, we're going to see exactly why that is. Now, one feature of Mplus is it can analyze data that is not given on the individual level, but with some sort of weighting or frequency. And this is what the coal miner data looks like. So we have the x variable, age, 22, and then we have, the first line of the data set represents age 22 not experiencing breathlessness, so u equals 0. We have 1,936 individuals, and then the second line of data represents age 22, u equals 1, and there were 16 people. So your data can be in frequencies. It doesn't have to be in individual data. Okay, so now before we look at the example anymore, we want to talk about special language to do with categorical variables in Mplus. And basically, the most important one is part of the variable option or variable command, and that's the categorical option. So the categorical option is used to specify dependent variables that are either binary or ordered polytomous variables. And it's only for dependent variables. Like we've said, the scale of the independent variables does not matter. So categorical option saying categorical are U1, U2, U3 means that the dependent variables U1, U2, and U3 are either binary or ordered polytomous, and the program determines which of those categories the variable falls into. Another difference between categorical and continuous data analysis is that we're going to be estimating thresholds rather than intercepts. And we'll talk about this later on, that intercepts and thresholds actually differ only in their sign. So if you have a threshold and you want an intercept, just change the sign of the threshold, and vice versa. Now, for ordered polytomous variables, they have more than one threshold. So a categorical dependent variable has the number of categories minus one thresholds. So if we have a categorical variable with 3 thresholds, then it will have 3 categories, it will have 2 thresholds. So we needed a way in Mplus to refer to the thresholds in the model command. So the way we do this is we take the variable name using the number sign added to the variable name, and then the number of the threshold. So if we have for U1, let's say it has 3 categories, it's going to have 2 thresholds. The first one is referred to as U1 $1, and the second one is U1 $2. And then let's say that we have the variable U2. It has 3 thresholds, so we know that means it has 4 categories, and those 3 thresholds are referred to as U2 $1, U2 $2, U2 $3. And for a binary variable has 1 threshold, and it would be referred to as U3 $1. Now, in weighted least squares estimation, we have scale factors, and these only come into play with growth models or with multiple group models. And when they are referred to, they're referred to in squiggly brackets by the variable name. So here we're saying that the scale factor for U1 is 1, fixed at 1, and the scale factors for U2 and U3 are free. And we'll see that when we look at multiple group analysis this afternoon. So we're going to be looking at this data using logistic regression and using probit regression. Here's the input for the logistic regression. Nothing new from yesterday. One thing for logistic regression, you have to say estimator equals ML. For categorical, here we have the categorical option, categorical equals U. And we have the frequency weight option, frequency weight equals W. So the weight variable in the data set that I showed you was W. So here we're saying in the variable command that the frequency weight in the variable is W, so that that data set gets expanded properly and then analyzed properly. So we have the new option categorical, the new option frequency weight. The default for categorical variables, the default estimator in Mplus is weighted least squares. And when you use weighted least squares, you get a probit regression. If you want logistic regression, you have to say in the analysis command, estimator equals ML. And with maximum likelihood in Mplus and categorical outcomes, you get logistic regression as the default, and there's an option to ask for probit regression. I think it's in the analysis command, and the option is the link option, and you would say link equals probit if you want probit regression with maximum likelihood estimation. And in the model command, it's very simple. U on X specifies the logistic regression of the binary variable U on the covariate X, which is age. So this is breathlessness on age. The only difference The only difference in specifying probit regression input between the left screen has logistic regression, the right screen probit, is we don't specify any estimator in the analysis command because the default estimator for categorical variables is weighted least squares, and that gives you probit. So the left screen output gives you logistic regression, the right screen gives you probit regression. Now, here are the results of the probit regression, of the logistic, regression, sorry, from the input on the left screen. So you see in the model results, U on X. So the estimate here, this is a logit. 1.025 is a logit. We have its standard error and then the z-test. So we can see that the relationship is significant and it's positive. As Banks said, that could be all that maybe you want to look at, is that there's a positive, significant relationship. But you can also look at the odds. So you exponentiate the logit, 1.025, and it gives you the odds. So as age increases 1 unit, which in this case is 10 years, the odds of breathlessness increases 2.79. So that's what you can look at that way. This is just summarizing what Banks said earlier. And then you can also go to a probability. So we can say that the probability of U equals 1 given X is equal to 1 over 1 plus e to the minus L. We know that L is beta 0. Oh, let me put this over here. So we can see where the results come from. Well, that wasn't it. All right, so we say here that, so L is minus, it's beta 0 plus beta 1 times X. So it's an intercept here, so it has the opposite sign. We estimate a threshold, but beta 0 is an intercept. So it's minus 6.564 plus beta 1 is here, 1.025. And here we're taking at age 62. We had divided age by 10, so it's 6.2. In the define command, we did that just to change the scale. And then we get the value of L from that, which is minus 0.209. And if we then take 1 divided by 1 plus e to the minus L, that's 1 divided by 1 plus e to the positive 0.209, we get a probability of 0.448. So the probability of experiencing breathlessness at age 62 is 0.448. So basically what we've done is we've done a logistic regression, we've estimated a logit, and then we've created the odds, the log odds, and then also the probability from that value. So that's all the different ways that we can look at the results of a logistic regression. Now for probit regression, it's a little bit different. So here on the right screen are the probit regression results. And here we have U on X, and the estimate is a probit, not a logit. So that's one difference. Now a probit cannot be exponentiated. So the only other way we can look at this is as a probability. And this should look familiar because this is what Bengt was showing you. We have the normal distribution function. So the probability of U equals 1 at age 62 is the normal distribution function time taken for evaluated for L, which is beta 0 plus beta 1x. And this is an intercept, so we need to change that to a threshold in probit regression. So it's minus tau plus beta 1x. If we evaluate that using the results over here, we get the value minus 0.1834. And if we look that up in a z table, we get a probability of 0.427, very similar to what we saw in the logistic regression. And there's a relationship between logistic and probit regression there by the constant c, where c is equal to the square root of the variance of the logistic density function, pi squared divided by 3. So if you multiply a probit coefficient times 1.81, it should be very close to the logistic coefficient. So they differ only in scale. Okay, so now we're going to take a look at another example where we have two covariates. So let's look at the top here where we have the logit. It's going to be beta 0 plus beta 1 x1 plus beta 2 x2, where x1 is going to be smoking versus non-smoking. x2 is years spent in the coal mine, and the dependent variable u is going to be lung cancer, where u equals 1 represents having lung cancer, u equals 0 not having lung cancer. And we can look at this as a logistic regression or a probit regression, where f is the normal distribution function for probit regression and the logistic density function for logistic regression. And that's all summarized there. Let's leave that there. Okay, so let's now take a look at, so we have our beta 0 plus beta 1 x1, beta 2 x2, and that's represented on the right here with, these could be probits or logits, depending on whether this is a probit regression or a logistic regression. So we have years spent in the coal mine here. On x2 is years spent in the coal mine. The probability lung cancer is the y variable. And smokers is x1 equals 1, and non-smokers x1 equals 0. So this looks very similar to what we looked at yesterday. The shift of the binary covariate just simply shifts the line, and like we see in ANCOVA. But now these are the probits and the logits. They're linear. The probability functions are nonlinear. So if you look at the probability of u equals 1 given x1 and x2, with x2 on the x-axis, x1 and x2 representing different probability functions, then you can see the nonlinearity of that, and also the similarity of the shift with the binary covariate, the shift of the intercept here. Now, when we have two covariates, just like we have conditional regression coefficients in linear regression, we have to make adjustments for the fact that we have more than one covariate. And so for odds ratios, the odds ratios are adjusted for one of the covariates. So here we recognize the probability formula, and that implies a log odds of what we see in the argument here, beta 0 plus beta 1 x1 plus beta 2 x2. So then we can get a log odds for x1 equals 0 and x1 equals 1. So if we do that, so for x1 equals, x1 equals 0, right here, if it's 0, beta 1 falls out. So the log odds for x1 equals 0 is beta 0 plus beta 2 x2. For the log odds of x1 equals 1 is beta 0 plus beta 1 plus beta 2 x2. So now here we have our two log odds. And if we go on to slide 40, we can see that the log odds ratio for x and u1 adjusted for x2 is equal to the log of the two odds that we talked to down here. And it just so happens that the log of the two odds is equal to the difference between the two log odds, which is beta 1. And if you look over here, you'll see that if you subtract those two, you come out with beta 1. So beta 1 is constant for all values of x2. So there's a constant odds ratio in logistic regression. And this is not something that you have in probit regression. So it is this constant odds ratio that makes you able to look at odds ratios with logistic regression and not probit. But it also is a constant odds ratio, which may not be the case that beta 1 is actually constant over all values of, in this case, x2 is age. So when you interpret these adjusted odds ratios, you need to take that into account, that the odds of lung cancer adjusted for age is beta 1 times higher for smokers than non-smokers. So you need to make sure that you specify it's adjusted, or the odds ratio adjusted for age is beta 1. So OR is beta 1 here, whatever value beta 1 is in your particular analysis. Okay, so now we have another example, which should we take that or not? Okay. So here's another example, and in this example, we're looking at the NLSY data for alcohol dependence and gender. So on this slide, this is all about the data. So this is observed frequencies, proportions, and odds ratios. And so here's age, first drinking, and it's adjusted for age, first drinking, male and female. This is the frequency data that we have, and then we turn them into proportions, and then from the proportions, we compute odds ratios. So this is what the observed data looks like. So this is no model estimation, nothing except just looking at descriptive information about the data. Now on the right screen, we're now estimating probabilities and odds ratios for the data using logistic and probit regression. I just want to see where I am here. Okay, so here we have the age first started drinking, and we have logistic regression for female and male and the odds ratios. And you can see the odds ratio is constant for logistic regression, like we said. And here in the probit regression, we computed odds ratios. We don't normally get this, but we wanted to show. What we notice over here in the data is that the odds ratios don't look like they're constant over the age first started drinking variable. They seem to be higher earlier and, higher later, and in the middle not as high. So what would be interesting is which of the models captures this non-constant odds ratio better, or is this just sampling variability and there isn't that non-constant odds ratio to capture? So if you look at the estimated odds ratios for probit regression, you can see they're not quite as different as the sample information from the descriptive statistics, but there is some variability. So, one thing to think about, a lot of people use logistic regression and think that probit regression maybe is not, quote, good or something, but really they're very similar, and probit regression does not make that constant odds ratio assumption. And once again, we have an example where actually the probit model had a lower chi-square. So you might want to take that into account. Now we want to look at one more thing here, and that's actually the results from the Mplus output partially. So basically left-hand side is logistic regression, right-hand side is probit regression. Here are the unstandardized coefficient, right here for male, let's say. It's 0.98, and that is a logit. Now, the unstandardized coefficient for probit regression is 0.50, and it's a probit. if you take the constant 1.81 that we talked about and multiply it by 0.50, you get 0.91. So that's very close to the logistic regression coefficient, or the logit. And you can also compare the two standardized, 0.51 for logistic regression, 0.48 for standardized. So you can see that they're very, very similar. And they're just two different ways of approaching categorical data. One is not really better than the other. Now, we definitely either have to stop, we have to skip one example, and you have a couple of pages, or we need to.
It's a very good point to stop, I think.
Well, you don't want to try? Okay. But
I think so.
You don't want to try. We were supposed to take the break there.
Oh, okay. Well, let's do it then.
Well, I mean,
Do you have energy for 5 more minutes?
And then questions?
Yes. Oh, they
all right. So then you
loving.
want to start at 46.
Thank you.
You're welcome.
So let's go to open the books on slide 46, please. So now you had a lot of fun with the example. So back to formulas, folks. Take a deep breath. And we have talked about these models in terms of probability curves. Probability that u is equal to 1 as a function of x is a curve because f is a nonlinear function. It's either the standard normal or the logistic distribution function. But there is an alternative formulation that could be useful at least as a conceptual thinking exercise. And that is the latent response variable formulation, as it says in the second paragraph of slide 46. And that is a useful way of thinking about the models because it actually then provides a way to move from the binary dependent variable case to the ordered polynomous dependent variable case, the ordinal case. And some people may prefer that formulation in its own right, but it comes down to the same thing in these categorical dependent variable models. So latent response variable formulation is considering a continuous dependent variable, u star. It's a continuous latent dependent variable. And you can think of it as a latent response variable, or response tendency. And you see it in the picture at the bottom right here on slide 46. And the idea is that when the tendency to respond is high enough, when it exceeds a threshold, which we call tau, the threshold that Linda introduced, tau, the Greek letter for t, when it exceeds the threshold, this response tendency, you will answer u equals 1. But if your response tendency falls below the threshold, you will answer u equals 0. So you can think about this in terms of, say, getting an educational achievement item correctly. U star is then the specific ability that you need to draw on to answer this item correctly. If the specific ability is high enough, if it exceeds a certain threshold, you answer it correctly. Otherwise, you answer it incorrectly. But it really makes a distinction then that u star could be very close to the threshold but still below it, and you answer it wrong. Or it could be just above it and answer it right. So it says that right and a wrong answer may differ very little in terms of u star. Or put another way, the people who get it wrong, who get u equals 0 as an answer, may be very different people, those who absolutely know nothing about this topic and those who are very close to answering it correctly. So u star is actually what you perhaps would want to try to measure, but you have a crude measurement device, the u measurement of that more perfect variable. So if you think of it this way, you have a linear regression. U star is linearly related to x. We have a new slope here, we call it gamma, and a new residual delta. And the point is, though, that we cannot identify this residual variance delta because we don't observe u star. We lose something when we only observe u star as a categorical variable. So we have to standardize by saying that the residual variance for delta is 1. And that is what we do in This is talking about probit regression. This leads to probit regression when delta is normally distributed. So when delta in equation 68, that residual, is normally distributed, then this latent response variable formulation leads to probit regression. And if you go through the formula 69 and 70, talking about the probability u equals 1, derived, it's the same thing as u star greater than tau. That's what we saw in the picture of slide 46. You get an expression 70 here for the normal distribution function, where we say that we standardize the residual variance to 1, and it's the probit model, where the slope, beta 1, is the slope gamma for the u star. So it's the same slope. And it's just that the intercept beta 0 is the negative of the threshold, like Linda was mentioning. Now, you could alternatively assume that delta in equation 68 has a logistic distribution, logistic density. And in that case, the latent response variable formulation leads to logistic regression. So f then becomes a logistic distribution function, and we get logistic regression. But in that case, delta has variance pi square over 3 that we talked about before. So we get that scale difference between the logit and the probit. Now, the latent response variable formulation is sometimes called on to derive some measures that we often use, quantities we often use for linear regression with continuous variables. And that is the matters of R square, standardized effects, R square and standardized effects. That can only be derived from the U star thinking. And this was described by McKelvey and Zavoyna in 1975 in Mathematical Sociology, and it's picked up in more recent books, like multi-level books like Snyder's and Bosker's, when you can go and do multi-level modeling of this kind of logistic and probit regression. So R square is then defined for the continuous response variable U star, not for the observed categorical, because you want really a continuous dependent variable to talk about R square. But it's the same explained variance in the numerator and total variance in the denominator. It's just that the total variance then has the residual variance, C, which is either fixed at 1 for probit or fixed at pi squared divided by 3 for logit. But in both cases fixed, just fixed for different values. So R square is given in Mplus, but you should think of it as a quasi R square, and it's an R square for U star, not an R square for U. Likewise, the standardized effect can be obtained as usual. So gamma hat in the second bullet here, gamma hat sub S is equal to the raw gamma hat multiplied by the standard deviation of x as usual and divided by the standard deviation of the dependent variable, which is in this case U star. This is the general formula for a regression slope standardized with respect to both the independent and the dependent variable. Now, effect size then from the effect of x is not easily gauged in the standard linear regression sense. As it says in the last bullet on slide 48, the effect of x on the probability for u depends on the x value. So if you look at the bottom here on slide 48, for an x change in this, you look at a low x here and a higher x for the rightmost vertical line. You see that a unit change of x for a low value of x does not increase the probability of u equals 1 very much. But the same unit change in the range for the high value of x gives a much higher output change or dependent variable probability change. So you have a weak effect versus a strong effect. In other words, the effect is not gauged easily by regression coefficients in this nonlinear regression situation that we're in for logistic or probit regression. So it's a little bit different thinking. Slide 48 says that we have to think a little bit differently about these three concepts when we do these nonlinear regressions of logit and probit. And I think we'll stop there and get to the ordinal case, polynomous case, after the break. So by that, let's invite questions and answers.
Sure.
Slides 38 and
38.
and 42.
Okay.
38 and 42.
It looks also beautiful to look at one probit, another constant. However, if you look at the other one, you see at first the difference is small, and then getting bigger, and then getting smaller. But when you look at here, it seems like it's not the case. One probit. So my question is, if we have projected like this, which one we should do? Which one is closer to your case? For example, for the minors, and maybe when they are younger, and the impact is more. When you get in the middle age, it's getting bigger. And then you're getting older, no matter what, you're going to get smaller. What is your situation? Which one is best?
So let me restate that so you can hear it in the back. So the question is about slide 38 and slide 42, although they don't relate directly, because slide 42 does not talk about probabilities but odds ratios. But the general point being made here is if you look at the probability curves here, Linda was pointing out that they are parallel curves shifted sidewise, which is the hallmark of a different intercept but the same slope, which is beta 2, same slope. And this gentleman's point was that it seems like in this range, x2 that's about here, there's a fairly big difference in the curves, giving a big probability difference, this probability difference here. Whereas for low values of x2, which would be in this example low age of age first started drinking, the probability difference is fairly small. And up here, the probability difference is fairly small. You would see that in the estimated probabilities in the alcohol dependence example, although we don't show those estimated probabilities there. So that's a function of the nonlinearity. Down here, there's very little difference between the males and females. That is, you can think of it substantively. If individuals start drinking heavily, say, at age 10, it doesn't matter very much if they're male or female. They're going to very likely become alcohol dependent, perhaps, or have equal probability of becoming alcohol dependent. Same thing if they start drinking very late, it's not going to be any gender differences. But if they start drinking at a certain age in between here, there's going to be a fairly large gender difference. So that is a function of the nonlinearity. So that is as it should be.
And if we turn those logits and probits into probabilities, then you would see that.
You would see that, yeah.
So we only give logits and odds ratios in this slide on the right. We don't give probabilities, but you could compute a probability for each value of age first started drinking, the probability of alcohol dependence, and then you would see those differences.
So we have a question over there.
The other way around, though. The odds ratios are more extreme at the outset in the empirical data, right?
I don't, slide 41, you mean? What we looked at. Yeah, they were more, well, in the data on slide 41, we saw that when we estimated or calculated, I don't know the right word to use to make it clear that it's calculated them, they were very much more different. But the model estimated values don't look so different.
Yeah.
But couldn't you include an interaction regression to get that?
I'm sorry, what?
Yeah, so the question is, can we, if you want to have a varying odds ratio, couldn't you include an interaction? Yes, you could. In logistic regression, you can orchestrate non-constant odds ratios by an interaction. So you have that stated here. on slide 40. If an interaction term for x1 and x2 is introduced, the constancy of the OR no longer holds. So, and actually, it was an interesting feature here in the estimated probit. There seems to be a trend of increasing odds ratios for higher age of starting to drink. So saying that there is less difference between males and females. If you believe the probit model, there's less difference between males and females for those who started drinking regularly at a young age than for those who started drinking regularly at a higher age. And that might be substantively interesting.
You see that in the probit's odds ratio estimates. You there?
Yeah, you see that. We're showing the same slide here.
Right there.
Right. Now, the observed odds ratios, we don't know how well estimated they are because you know that they're estimated for different numbers of people in the different age categories. So we don't know. There's different amount of sampling variability in them. Yes?
Despite what you say, could you also, or might you, also explore interactions in probit? Nothing's preventing you from doing that, right?
That's right. You could have interactions also in probit, and the probit might then pick up the observed odds ratios even better. So, although it does a pretty good job here given the huge sample size.
Although we don't,
quite possible, yes.
Right, we don't usually include interactions in our examples, but they can, of course, be included as a covariate wherever one would think that they're important.
And you just use the define statement to create the product, yes.
Yes?
I know you'd like to keep the data between 0 and 10, but is that your general preference or is it specific for Mplus?
Wait, you mean the variance is between 1 and 10?
Oh, no, okay, I see. Maybe then I got confused with variance
So
versus...
are you confusing probabilities between 0 and...
You had divided age
Right.
for coal miners also by 10, so that's why I was trying to say, oh, okay, age is going to be
Oh,
between
no.
0 and 10. So.
Yeah.
No, that's not an essential matter. It's, yeah, not at all.
Not at all, right.
Okay, more questions, yes.
Yeah, what's the reference category in these like logistic equations?
It's 0. So you model probability u equals 1. So it's always related to u equals 1 related to u equals 0. So that's the standard in the binary logistic regression. Unfortunately, the standard in the multinomial polytomous regression is that the reference category is the last one. And we were thinking about, when we started this, we were thinking, should we set the record straight? No,
Or
that's going against the traditions a little bit too strongly.
The age, the reference category for age, for example, here?
Well, age is a covariate.
Yeah, no, so this is, we're looking at the relationship. The odds ratio has to do with the relationship between gender and alcohol dependence. So we're only talking about the reference category for not dependent and for female. But age, we don't work with any reference categories there. It's just continuous. So this illustrates that the odds, that we're dealing with a constant odds ratio for different values
of age.
Adjusted for the age. Again, think of an odds ratio. Well, let me say this. It might be useful. An odds ratio has to do with the relationship between two variables. In this case, gender and alcohol dependence. An odds is a descriptor for a single variable, alcohol dependence. So OR is two variables, O is one variable. So when we say OR here, you have to think, well, which two variables are involved? Well, it's the X variable of gender and the dependent variable U of alcohol dependence or not. So this is good, you know, to exercise this thinking early on here. Yeah, more questions. Bruce.
I'm not sure, but I think you just said that in the polytomous model that you use an adjacent categories approach as opposed to proportional odds. Is that right?
No, I didn't mean to say that. So the question is, with polytomous items, which we're going to talk about after the break, there are several different logistic models that you can entertain. We're going to use the proportional odds model, which is the most common. But it's adjacent category approaches as well that you can take. Now, I was just saying that the reference category when you have polytomous response is the last category, whereas in binary logistic regression it's the first category. U equals 0 being the first, U equal 1 being the second. All right. Yes?
Slide 35 and 36.
35 and 36.
I feel really comfortable with how to interpret logit outputs and how to switch it to the odds ratio by exponentiating it, but I'm having a harder time understanding how to interpret the probit output. And I was hoping that you could explain it a little more. I see where the threshold got turned into the intercept and it's the slope, but I'm not really sure where that 1.6 or 6.2 came from. And then you said you looked in a table for that. And
6.2 is the value of the covariate, age 62. So you know, the regression coefficient is 0.548, and it has to be times a value of x1, or times x, I guess, here. So the x value is 6.2, which is age 62, because we divided age by 10 in the define command.
Let me just repeat the basic questions. So this lady feels very comfortable with the logistic interpretation of the logistic regression results, but less so with the probit. And we see that very often. And the reason is that probit, you know, there were three steps in the interpretation: sign significance, odds ratios, and probabilities. The middle one, the odds ratios, is not easily used for probit. So maybe that's why you don't feel as comfortable. But to make you feel more comfortable, just focus on this. U on x is positive and significant. And if you insist, yes, we can turn it into probabilities like we do on the right slide. We can compute odds and odds ratios, but they won't be constant for given values of other predictors. But if you have the sign and significance and the probabilities, you essentially have all that you need. More questions?
Yes.
Yes. Oh, sorry.
Oh, sorry.
You go ahead.
27 and
35.
So, okay. Oh, 42?
I was just wondering about the p-values for extra models, and also you said that the right one, the probit model, was better, and then on this side, the ESEM model that was better.
Okay, so why are we saying, okay, the question is about, I think, why we said the probit model was better on these two slides. Is that the question? Just looking at the two chi-square values, the lower the chi-square is, the better fit of the model. So probit has a lower chi-square on both of those. So that's why we said that.
Okay, and so you mentioned the p-value for the first logit model, but then
So we said it was great. Right, we just didn't give the p-values for the others.
okay.
I don't, is there a reason, Bengt, that you didn't do that?
No. So we're talking about slide 42. We don't have p-values here, but you can go into a chi-square table and look at them. And they're probably, this is probably a significant misfit. You know, p-value is probably very small. But on the other hand, the sample is very huge. And all we wanted to say that the probit had a lower chi-square than the, probit had lower and better chi-square than the logit. But we weren't really interested in testing it. And your homework, folks, and we'll give you the answer in March, is how you calculate the degrees of freedom.
Oh, that's mean.
Is that mean? Should I tell them? Okay, so I'll tell you. So why do we get 7 here? Well, age 0 has 2 parameters, right? Intercept and slope. Age 0 has 2 parameters. I'm talking about slide 27. What is H1? H1 is the product multinomial, meaning that for each age, we have a binary outcome. So for each age, since it's binary, we have one probability parameter. For each age, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9 ages. 9 times 1 is 9. 9 parameters in H1, the unrestricted product multinomial, or binomial in this case. 9 minus the 2 H0 parameters is 7. And then your task will be to do the same calculations for slide 42.
Now that's more fair.
Is that fair?
Yes, I think so.
Okay. So one more question before break.
It's kind of a follow-up to this one. So when you're talking about the logit and the probit model, it seems like you kind of did both and then compared. How do you decide which one to do usually?
So the question is, we're talking about the logit and probit, and how do you choose which one to present? Anybody?
Well, in some disciplines, logistic regression is just what is used, and odds ratios are very important in certain disciplines for talking about results. So I think it would be hard to buck that trend, and unless you had a reason, unless you could say, if you look at this with probit regression, you draw different conclusions, which is pretty unlikely. They're very, very similar to each other. So, and you might want to use probit regression, probit versus logis in factor analysis. So, these are going to be your factor loadings. They're going to be probits or logits when we look at a factor analysis model. And whether you use weighted least squares or maximum likelihood for a factor analysis model depends on how many factors you have, how many items you have. Certain estimators are better for certain situations. And then you just fall into probit and logit.
So that's a good question. So let me answer it, just add to Linda's answer, or say it one more time. Like half a century ago, there were hot debates between probit fans and logit fans. Today, I think you should think of this as a closed case. Either one of them is just fine. So in these univariate regression cases, there is more commonly the logistic regression is used. So just use that. Don't think that you have to sit and test these models. If you don't have constant odds ratios, throw in the interaction between x1 and x2 in logistic regression. But note that probit regression would have been just as good, which is good to know when we move to multivariate dependent variable models like factor analysis, where in some cases there are distinct advantages of the probit approach, because the probit model has some more generality to it when it comes to several dependent variables. And that has to do with, for those of you who are statistically minded, that there is no natural multivariate logistic distribution. There's no natural multivariate logistic distribution, only a univariate one. Whereas for probit, there's a very natural multivariate distribution, namely the multivariate normal. So it's easier to generalize probit models. All right, should we take a break?
Yes, and let's start promptly at 10:30.
Promptly at 10:30. Okay, are you ready for more formula torture? Yes, that's the spirit. We do it because it's hard. So let's land on the moon here a little bit more. Okay. So last time we spoke, our hero was working with a latent response variable formulation, and it was a motivation for generalizing the binary response model to polynomous situations. And it also provided an alternative way to think about the standard probit or logit regression. Now, the latent response variable formulation would be used to explicate what we have on the left screen using the right screen. So the left screen is slide 49, and let's talk about the ordered polynomous case first in terms of the left screen and then in terms of the right screen. It's equivalent, but it's two different ways of looking at it. So let's say now that U is polynomous with 3 ordered categories. So high, low, medium, high, for instance. And so we have then U, probability of U, as a function of x, can be represented by, in this case, 3 curves. So you have the probability of the highest category going up just like before. When we only had 2 categories, we plotted U equals 1 here. And of course, we could have plotted U equals 0 as well in the binary case, and it would have started high and gone down as the complement of U equals 1, making those probabilities sum to 1. So, but here we also have a medium category, U equals 1, where the probability as a function of x first increases and then decreases. So you can do these kinds of probability plots either by hand or by some software, or you can do them in Mplus as a result from the estimated model. So you can think of this as for low x values, it's most typical that you are answering in category u equals 0. For medium x values, well, u equals 1, that category becomes most prevalent. And for high x values, u equals 2 category becomes more prevalent. So these are describing the probabilities of the 3 categories for u. Now you can look at this slightly differently, which is done in the proportional odds model variation on the logistic modeling theme for polytomous items shown in the Agresti book. And that would be to look at probability of u equals 2, the highest category, and probability u equals 1 and or 2, u equals 1 or 2, so falling in either of the 2 highest categories, and which is a higher probability for any given x value, so a higher probability to fall into either 2 or 1. So the hallmark of this proportional odds model is that if you look at the highest category probability and the 2 highest, and when you have more than 3 categories, the 3 highest, or you can go from the lowest end, then those probability curves become parallel. It's an assumption of parallel curves, which means that they are only shifted by an intercept and the slopes are one and the same. So if you do it in a logit version, instead of the probability, you plot the logit, which is this complicated expression here, the logit. You can write logit here. And then you have 2 parallel lines for those 2 kinds of events. So often this proportional odds model is just presented like this with the assumption that you have parallel lines here, which is not very intuitive, right? It's not very intuitive. Why would that be a reasonable assumption? So that's why we borrow from the latent response variable thinking and get a more intuitive interpretation of that situation. So on the right, you have the same situation. You have 3 categories, u equals 0, u equals 1, and u equals 2 in the top left picture. And you observe then u equals 0 if you have a low value on the u star variable, the latent response variable u star, which again is assumed to be linearly related to x with the residual here, delta. So if u star falls below the lowest threshold, tau 1, you get u equals 0. If it's above the highest threshold, tau 2, you have u equals 2. And if you're in between of the 2 thresholds, you have u equals 1. So you expand on the notion of that crude classification of the u star variable. U star is what you would like to measure, but you don't want to put the respondent under so much strain to give a continuous score, but instead just, in this case, a trichotomous score, 0, 1, 2. Now, if you assume then that you have this situation of a continuous response variable, and you have 3 categories for the observed variable, you have 2 thresholds, then this formulation, if you assume a logistic density for the residual, will give you what you have on the left. It will result in what you have on the left, including the parallelness of the 2 sets of probabilities there. So you can go through the formulas and see that that holds, but you can just accept it, and that may be the easier way to go about things. Otherwise, you have to go through these formulas here. But I'm not going to go through them. I'll just show you that that's a way to prove that you get what you have in equation 81 and 82. You have the same same slope gamma, which is the parallel curves, right? Same slope, but with different thresholds, tau 1 and tau 2, for those 2 probability statements. I'm talking about equations 81 and 82. So you can go through those formulas and enjoy that algebra manipulation. Stat 101 and high school algebra is all you need. Same for logit for ordinal variables or the categorical variables. Again, slide 53 bottom says, note same slopes or parallel probability curves. And that's an important notion of the same slope. Same slope is, for polynomous responses, only happens when you have ordered categories, not when you have unordered, which we'll turn to next. Unordered categories gives you several slopes, one for each category. But this gives you only one slope. And the reason is why you only have one slope is because you think that you have only one latent response variable, so only one regression slope here multiplying x. And it's just so that, just the case that u is then related to different segment of the u star variable. So this one slope is the hallmark of the ordinal model. So you can have the ordinal model also for probit. So you have the logit and probit choice there once again. And again, like Linda said in Mplus, under maximum likelihood estimation, the default is the logit, but you can say link equals probit, and then you get maximum likelihood under the probit model. So you can take an example here. There's a famous alcohol study called the Alameda study. And I actually have Alameda scoring. I think that's how you pronounce it. Yeah. Anyway, so quickly, I'm not going to go through this in detail, I think.
You can. You should.
Okay, I'll go through it in detail. It's very helpful to have a person sort of time you. If you run a marathon, you don't want to run too fast or too slow. All right, at any given point. So, alcohol consumption, ordered polynomous regression, sponsored by NIAAA, no doubt. So, on the days that you drink, how many drinks do you have per day on average? On average, I guess it should be. So, you have an ordinal U. How many drinks, it's really continuous, or as we will see shortly, count outcomes. You count how many drinks you have. But very often, that variable is categorized. So 0 is non-drinker, 1 is 1 to 2 drinks per day, 2 is 3 to 4 drinks per day, and 3 is 5 or more drinks per day. Because these categories are I assume more meaningful from a substantive point of view to alcohol researchers than the original counts. So I think 5 or more drinks per day, for instance, is referred to binge drinking. Sometimes it's 6 or more, I think. So it's to sort of push it over into using a whole 6-pack, I guess. But so this is a scoring then that is not representing a continuous variable nor a count variable, but an ordered categorical variable would be very suitable. And then you have age in years and income here in categorized, but still treated as a continuous interval scale variable. Yeah, focus on 713 males with regular physical activity levels, and here is where it was discussed. Mutia 1993 is from a book, that edited book by Bolin and Long, testing structural equation models, I think it's called, that I referred to yesterday. By the way, any Mutian reference that we talk about can be found in either of two places. One, the first one you should look at is on the Mplus website under papers, or otherwise, if you don't find it, on my UCLA website, which you can get to through the Mplus website. You click on About Us, and then you see Bengt Mutian, and then you go into the UCLA website, where you may have some more older references sitting there in PDF form. All right, so going forward, and we are honored by the presence of our host. Do you have anything you want to say, Nick? No? Now, here's the model written out. Probability U equals 0, 1, 2, 3 by the formulas that we agreed on, right? And you see then that here we're talking about getting probability between the area under the curve between the threshold tau 1 and tau 2. It looks like a difference in normal distribution function values. Let's not focus on the formulas right now, but instead look at a picture. So ordered polytomous regression really has some assumptions embedded in them, which may or may not hold. And again, as Linda did, you can, for large-scale data at least, get a notion of their reasonableness by plotting probits or logits in the sample. So here we have sample probits plotted in line with how Linda did it for the British coal miners. And you have then a plot of the highest category, u equals 3, as a function of h, which looks somewhat linear, and u equals 2 or 3, which is the two highest categories, and u equals 1, 2, or 3, which is the combination of the three highest categories. And according to this proportional odds logistic or probit model, those plots are supposed to be linear and parallel. So that, for our purposes, looks pretty reasonable, that assumption, the drinking related to age. But look at the drinking related to income. It's not linear, and they're certainly not parallel. They have different slopes. So the bottom picture illustrates the fact that we can have a violation of the assumption behind the standard proportional odds ordinal logistic or probit model. The logistic model would also be problematic. So in this case, the assumptions don't hold. Now, typically, I would say people don't even look at this. They don't even bother to check this. But they should, I guess. And if this is the case, you may want to abandon the ordered model and use an unordered model. And in fact, in future Mplus, we will try to allow for models that have a partially ordered model. Actually, I used to throw this out as an example around early 90s for a dissertation to come up with a model that had the mixed ordered, unordered feature. Excuse me. Nobody jumped on that offer. And then Don Hedeker, this excellent statistician in Chicago, actually developed a method to do that. So if you want to do that, you can actually use his program for doing it. But it will be coming in Mplus at some point. That was the example. Now we go to the unordered case, a new topic, folks. So let's take a very deep breath. And my timekeeper says we're on time. So the unordered case is also called nominal. Nominal response variable, nominal dependent variable. And as I alluded to, we're going to see a lot of those when we get into latent class mixture model. Here, however, we're going to talk about an observed nominal variable. So particularly econometricians, transportation researchers are very fond of working with those kinds of dependent variables. And so are people in the business research area, marketing research, and there are many good econometricians who have contributed to these kinds of models. None of their names come to my mind, but they'll come later, I hope. Anyway, so here in all its glory, equation 91 looks at first glance unpenetrable, right? But it will become your friend very shortly. If you look at it long enough, it's not too complicated. What does it say? It talks about the probability of a U variable for individual I, assuming or being observed in category C. So that could be like taking the bus to work instead of taking the car or the train. For given values of X, like the person's age, education, distance to work, or whatever. It could be a whole set of X variables. And again, we work with our favorite e to the power of construction in the numerator, which has an intercept and a slope. Intercept beta 0 and a slope beta 1. But we see that the intercept and slope are also subscripted by c. namely varying across the categories of the dependent variable. And the key issue is that the slope varies across the categories, which not only the intercept, but the slope as well, which it did not for the ordered categorical case, right? Now, the denominator, you could ignore for now. It just makes certain that the probability lies between 0 and 1. So it's a normative feature. Now, we have then k categories for the u variable. And we talked earlier about a reference category. In this case, the reference category is the last category, cap k. So in equation 92 and 93, you see cap k appearing for the intercept and the slope. And those two, intercept and slopes, are standardized to 0 for the last category. So we do not estimate those parameters. And if you do that, the interpretation is as follows, that the model in 91 implies the log odds, and we know that a log odds is the log of the odds, and in this case it's the odds of being in category C, the category that we're talking about, relative to the reference category, the last category. So the log of the odds of observing category C relative to category K is a linear expression in X with slope beta 1c. So we're going to be able to interpret beta 1c in terms of log odds. And once again, we can instead talk about odds by taking e to the power of beta 1c. So it's very much the same interpretation as the binary case, except that we tend to more explicitly say that we relate our odds for the category that we're considering, C, to the last category. Last category being sort of a normative category, as we will see in applications. Now, there's a very direct relationship between the multinomial logistic regression, which is for the unordered polytomous case, and the binary logistic regression that we started the day with. In fact, the multinomial, a special case of that is when we have two categories only. If you look at that expression 91 for two categories, slide 59 says that it looks like this. Because the last category, if you look at the denominator, the sum in equation 91, the last category k has coefficients 0, and e to the power of 0, e to the power of 0 is equal to 1. All these nice high school concepts. So you have that 1 sitting there. And if you multiply the upstairs and the downstairs by the same quantity, you get down to this expression here on slide 59, second line from the bottom, which is the standard logistic regression. So the standard logistic regression can be expressed as 1 divided by 1 plus e to the power of minus, or e to the power of plus divided by e to the power of plus 1. So this expression top and bottom of slide 59 are one and the same thing. So sometimes in books you see this expression at the top, which comes from the multinomial logistic regression. Sometimes you see the one at the bottom, but they're one and the same thing. Same interpretations. And I'll stop there and hand over the microphone to Linda.
Thanks. Okay, so now we're going to look at an example of how you would do a multinomial logistic regression in Mplus. And the new option is the nominal option. So you need to let Mplus know that you have an unordered categorical variable, a nominal variable, by listing the variable that has those specifications on the nominal, using the nominal option. So we say nominal equals u, and that means that we're going to be estimating a multinomial logistic regression for the variable u. In our model command, we say we regress u, and in this example, u is antisocial behavior type of variable, and it has 4 unordered categories related to different types of offenses that people can do. Property offenses is one category, drug offenses, person offenses, and then no offenses. And the 3 covariates, X1, X2, and X3, are age, male, and black. So it's very simple to set this up in Mplus, and we'll take a look at what the results look like. Actually, I'll do that over on this screen. So as Bengt said, if we have 4 categories, one is the reference category. And as he also mentioned, we get more than one set of slopes, or more than one slope for the dependent variable. So here in the output, you see we have U number 1, U number 2, U number 3. So this is how we describe which category it is. And U number 4, of course, we don't see because it's the reference category. So here we regress the first category, U number 1, on the 3 covariates. Here's the second category and the third category. And I think the first category is property offense, if I'm not mistaken. Actually, let me put that over here so I can double check so that we are talking about the right thing. Right, so property offense is category 1, drug offense is category 2, and person offense is category 3, with no offenses being the reference. Now, related to that, in Mplus, we give you results using each category as the reference category. So although in the model results, we use the last category, we do a translation post-model estimation. So if you don't want the last category to be the reference category, you can use some of the results using other reference categories. So what do we say here? So we have category 1, the property offense category. And what do we see? If we look at the third column, we see that 2 of the covariates have significant relationships because the z values are larger than 1.96. One significant effect is for age 94, and one is for male. So how we interpret this is we would say as the age variable increases, the likelihood of being in the person class versus the no offense class decreases because that's a negative coefficient. So the likelihood of being in the first category compared to the last category decreases as age increases. And here that we have a binary variable male. So for males, in comparison to females, are more likely to be in the property category than the no offense category. And then you just go through the same type of interpretation. You see that for the drug category, we have 2 significant covariates. Age is also significant, but positively, and being black is negative. So you do the same type of interpretation. But we have 3 sets of slopes, not unlike treating an ordered polytomous variable where you only have 1 regression slope. We have regression slopes for each category. Now, what can we do with this information? Well, we can turn them into probabilities. And this is in chapter 13, in case anybody wants to see a fuller explanation. Yes, it does. I suffered over that chapter. It's still not quite up to par. But anyway, so in the first example, let's assume that all the x's are 0. So then what is our logit? Our logit is equal to just simply the intercepts. So if all the x's are 0, then beta 0 is plus everything else is 0. So it's just beta 0. So here are the values. The log odds are taken from the output. We can exponentiate them and sum up those values. And then the probability is just simply the exponentiated value divided by the sum. And so we can see the probability for individuals where all the x's are 0, and who would those people be? I think 0 for age represents 16, if I'm not mistaken. And then 0 here would be females. And for the black, 0 would be everyone other than those who are black. So that would be the people we're describing. So these are the probabilities for those people of being in the different categories. So for example, for those people, the probability of being in the first category, which I can never remember what it is, property. Right. For being in property is 0.069. So this is what you can do. And then you can look on the next slide at a situation where all the x's are 1. And when all the x's are 1, these are black males age 17. So when all the x's are 1, then the probabilities that we compute, the logit is more complicated. So besides the intercept, we have minus 1.82 for category 1 from here, plus the regression coefficient up here, minus 2.85 times 1, plus the regression coefficient 2.578 times 1, plus 1.158 times 1. So this is how we compute the logits. It's just beta 0 plus beta 1 x1, beta 2 x2, beta 3 x3. And we do that for the 3 categories, other than, and not the reference category. Then we get, so the log odds is 0.629 for category 1, minus 1.098 for category 2, 1.817 for category 3, and 0 for category 4. We exponentiate the values, sum them up, take the probability exponentiated value divided by the sum, and we get the probabilities of 17-year-old black, for 17-year-old black males of being in the various categories of offense. So 0.20 for property offense, for example, 0.67 for I don't know why I can never remember these. Pearson, and 0.036 for drug. And then you can further take this information and turn it into a diagram where we summarize the information about the 2 covariates and the dependent variable. So this represents 17-year-old black males, their probabilities of being in the various categories. So by age. So age is on the x-axis. So class 1 is the property class, or not class, but category. And you can see that at age 16, that's the category that black males at age 17 are most likely to be in.
Class 3.
Oh, class 3, sorry. Okay, so that's Pearson offenses. So we have Pearson offenses here, and then we have the, I can't even make out the little things. That's the, okay, Pearson, property, drug, no offenses. And then you can see as age changes, as age increases, at different ages, things switch over. So you're more likely to be in one category than the other. So you can take the information from your output, turn it into probabilities, and then use that information to better understand the relationship of the, all the 2 covariates and the dependent variable. And I think it's your turn again. I'll hand this over to you.
And I remembered the econometricians' names now.
Oh.
So they are two important ones are McFadden, F-A-D-D-E-N. who is in the marketing area more, and Madala, who is an econometrician, who has written a very nice book that's in the reference list, Madala, M-A-D-D-A-L-A. And he has a book that specializes in strange dependent variables, of which we are covering quite a few this morning. Here's another one. So now let's say that you have a model that is, or a dependent variable rather, that looks like this. You have to sort of, I'm talking about slide 66, and you have to tilt your head like this and look at the distribution of y. It looks like it's fairly normally distributed, but then it has a big piling up here. This is a big piling up, a floor effect. In this case, a floor effect. So a variable that is limited in its range and is continuous if it's above 0, but has a big pile of people at 0, say. And for instance, the typical example is in a James Tobin article, which talks about consumption of durable goods. Doesn't that sound econometric and good? Consumption of durable goods. So a durable goods example is a refrigerator, which just broke after 16 years. So in this year, we will consume, we'll spend money on a refrigerator, at least a part. How appropriate. That's why it broke down. Now, but for many people in 2009, and this is the year we're in, to remind you, there will be many people who don't consume on refrigerators. Those lucky people are in the pile here. And some will have to pay a little bit, like we were replacing the compressor. Some others have to buy a whole refrigerator, which is far more expensive and will get you into all kinds of parts you don't want that will break down. Just to give you advice on refrigerators on the side here. We're a full service operation. But what you really want to do then, in that case, when you have that strong floor effect, and this will be a theme that we come back to for the rest of the day, you certainly have non-normality, but you don't want to rely on non-normality robust inference techniques like non-normality adjusted standard errors and chi-square test of model fit. That's not enough. You have to change your model. Your model has to change. It can no longer be a linear model for y when y has a limited range like this. And there's a lot of arguments in econometrics for that I refer you to the literature for. But instead, you can work with a continuous response variable thinking, a y star, that has a nice linear equation with an intercept, in this case, called pi 0, and a slope called pi, and a residual called delta. In this case, since in this case then, y star is observed, if you look at the right screen, is observed for those who actually consume. But when y star falls below a certain level, you will have no consumption at all. So it's sort of a crudely observed variable, which is y is observed. Here's a very general case. You have a lower censoring point and an upper censoring point. But let's assume we only have a lower censoring point. If y star is low, you observe the lower censoring point, which is in our refrigerator example is 0. So you have a lower censoring point only, and it is 0. So if y star, which is your tendency to consume durable goods, falls below 0, you don't have enough urge to buy a new refrigerator. You are satisfied with your dirt cellar. Then y star will, or the y will be observed as the value of 0. And only if y star exceeds the 0 point do you observe y star as, is y observed as y star. So y star is a latent variable that becomes observed above 0 when you start consuming, and otherwise is just fixed at 0, piling up at 0. So that's called, because of Tobin and probit, Art Goldberg called that Tobit modeling. And Tobin was not happy with it, I heard. But that's just gossip. Tobin went on to win the Nobel Prize in economics. That's when you get to go to Stockholm. Any case, you have then it's an interesting model because it has two parts, and we'll see that feature coming out in several different models that we can look at. One is the probit regression, the probability. You can actually model the probability of consuming. So the probability of consuming versus not consuming is what the first equation says. And that's a probit regression derived from this model at the top. And for those who consume, you can formulate a conditional expectation, a regression function. Although it's no longer linear in x, you have more than this linear part in 65, second line from the bottom. You have a nonlinear part, which is a so-called hazard ratio, or actually it's called a Mills ratio. The density, normal density divided by the normal distribution function is part of that. So it's a non-linear regression for y among those who consume. Now the weakness of this model is that it assumes that you have the same x's and essentially the same slopes influencing both the decision to consume or not and the amount of consumption. Now, that's a restriction that can be relaxed in other models that we will look at. That's called a censored normal regression. Now, folks, we get into exciting stuff here. A count-dependent variable. I think that's an underappreciated model, which we try to get people to use more. So here's a situation where you look at, for instance, if you take an alcohol example, in the last 30 days, how many times did you drink 5 or more drinks in one sitting? In the last 30 days, how many times did you drink 5 or more drinks in one sitting? That is the binge drinking type of question that you try to get college students to answer, and you look at trends in that over time. So, when you work with DSM, you know, the Diagnostic Statistical Manual for Mental Health Problems, any kind of DSM has a lot of criteria, and if you have a sufficient number of criteria, you get a diagnosis as having a problem of a certain kind. So the number of criteria, diagnostic criteria fulfilled, would be another example of a count. The number of diagnostic criteria fulfilled. So typically then the distribution looks like you have here, high piling up at 0. The event is pretty rare. So a lot of people say it never happened in the last 30 days that I drank 5 more drinks. And some people will fall into the 1, 2, 3 categories. The tail drops off very quickly here for a typical count outcome. And that's described, and these rare events models for counts is described by Poisson regression. And the dependent variable, u, the count variable, which is 0, 1, assumes value 0, 1, 2, etc., can be described by this expression here, which is using our familiar e to the power o, and in the denominator we have r exclamation mark. And that doesn't mean that we're excited about it, but it's a r factorial, or in European language, facultet. So if, for instance, r is 2, that means 1 times 2. So we're teaching you a lot of high school mathematics as we go by here, too. In any case, lambda is the key parameter. Lambda is the rate at which a rare event occurs. It's the rate is equal to the mean count. This is a new addition that you don't have in your handout, but we have here on the screen. So you can add this statement, rate equals mean count. But write neatly now. So that's the mean, and the higher the mean, the higher the bars will be over here on the right. And if the mean is really high, like 10, this distribution is going to start looking like normal. So when you have a very highly prevalent type of event that you're considering, the count distribution looks quite normal, and you could approximate it by the normal. but very often it's rare. So the key parameter is lambda, the rate or the mean, but statisticians, again, they insist on taking logs of things and making life difficult. So the natural log, the E log, is what we're looking at. That's called ln. ln of lambda is what we assume the standard linear model for intercept beta 0 and slope beta 1. So it's a log rate equation. So when x changes, beta 1 tells you how much the log rate changes. Not the loaded, but the log rate. And since it's the log rate, coefficients will come out looking funny because say x is 0, then the rate, lambda, would be e to the power beta 0. So a large negative beta 0 would correspond to a rate that's e to the power minus something large, which is a very small value. So a large negative beta 0 would give you a very small rate, a very highly peaked at 0 count distribution. We'll come back to this, in topic 6, growth mixture modeling with Poisson count outcomes. Crime curves, for instance, the number of offenses in the last year are often modeled in terms of this Poisson distribution. Now, the only problem with this Poisson distribution is that it doesn't fit data very well. Minor detail. And the problem is that the Poisson assumes that mean is equal to the variance. That's built into this distribution. But data often have variance greater than the mean because the preponderance of, you have a high degree of zeros, and the only way the Poisson can cover the case of high degree of zeros is to also raise the bars for the positive numbers. But that is not what the data has. So statisticians have come up with a ZIP, zero-inflated Poisson regression. And that's an interesting model because it is our first instance of a mixture, a latent class, a finite mixture model. So we're going to take the alcohol example here and say, let's consider two kinds of people. People who don't use alcohol and people who use alcohol. So people who don't use alcohol, and well, first let me back up. And we're considering the count as, again, the number of times in the last 30 days that you drank at least 5 drinks in one sitting, the binge drinking. Number of times in the last 30 days that you engaged in binge drinking. Well, those who don't drink alcohol will have the count of 0, right? Count 0. And we can talk about those people as the 0 class. On slide 69, 0 class. And we will only see u equals 0 for that class, right? Probability in the 0 class where only u0 is seen. People are in that class by probability pi. So in the population, I don't know how many non-drinkers there are, but that would be pi. And then we have the other kind of person who is a drinker. We have probability 1 minus pi for being of the drinker kind. And for the drinkers, we will assume that the counts follow a Poisson distribution. So for those people, we can observe u equals 0, or 1, or 2, or 3, etc. What that means is that if you observe u equals 0 as a response, that could happen for 2 reasons. 1, the person is not a drinker. 2, the person is a drinker but didn't happen to binge drink in the last 30 days. So you have 2 reasons for being at 0. So probability u equals 0 is a mixture at 0, as it's called. Probability pi that you are a non-drinker plus the probability that you are a drinker, but you happen to drink with u equals 0. And u equals 0 gives you e to the power minus lambda. If you look on slide 68 at the top, if you put in a u equals 0 here, u r equals 0 here, you will see that that gives you e to the power minus lambda. So it's a mixture at 0. That will then be able to capture a high peak at 0 and a variable that has mean greater than the variance. Actually, the mean, you see the mean count, these two things are added on the, in the PowerPoint presentation here and not in your slides. Slide 69, the zip mean count is lambda times 1 minus pi. The zip variance is lambda times 1 minus pi times a factor 1 plus lambda times pi. So that's something that is greater than 1. So the variance, the second term, greater than 1 means that the variance it can be bigger than the mean, which is what we want.
Could you put that up on this slide as well?
Yes, sorry. So here I'm talking about slide 69. These two parts are added last minute, not in your handout. And again, now we have a model that has two parts to it in terms of interpretation. So the zip model, first of all, has a logistic regression part. The second line from the bottom, logistic regression, the loaded for pi. We know what the loaded for pi means. It's a log of the odds of being in the 0 class, the non-drinker, versus drinker. And that is expressed as a linear logistic regression with an intercept gamma 0 and a slope gamma 1. And we regress it on some x variable, whatever relevant x variable we have, like age is a typical one, or gender. And that tells you who tends to be who tends to be a non-drinker. And then it implies for those who drink, who are in the drinking class, in the second class, those who are not in the 0 class but in the other class where U follows a Poisson distribution, for those we express the log rate, just like in regular Poisson regression. The log rate is a function of x. And we notice then a very important thing here, that beta 1, the slope for the log rate, is different than gamma 1. And it can even be different x variables. So the decision to not drink or not drink is based on different background factors than the decision on how often to binge drink if you are a drinker. So that kind of flexibility cannot be covered by the censored normal distribution. So that's a strength of this. So for instance, if you have planning on intervention in schools, the intervention may be treatment control, may be the x variable, and you may have different effects in the decision to drink at all versus binge drink of the intervention. So for instance, gamma 1 may be significant but not beta 1, for instance. So you have much more flexibility. The zip is pretty good. Now, you also, for completeness, faster is this. That's important. Lena's trying to give me signs of going faster or slower, but she has mixed them up. So, all right. Second day's, well, it's not afternoon yet, right? Is it? All right. So negative binomial regression is an alternative to zip that's talked about more and more, and you should know about it. It's an interesting idea because in that case, the log rate has an additional term, epsilon, that is a residual. So we're saying that even if you have two people have the same gender and age, their rate for the count, binge drinking, differs as a function of unknown, unobserved covariates that are put together in epsilon. So people differ with respect to epsilon, capturing heterogeneity with respect to epsilon. So the negative binomial, so back to the Poisson, where the mean and the variance are one and the same. The negative binomial has different mean and variance. You have an alpha parameter in the negative binomial. You don't have to go to a zero-inflated model for the negative binomial to be able to cover the variance being different than the mean. So negative binomial, as it says in the text segment, with alpha 0 gives Poisson. Alpha is called a dispersion parameter. It's greater than 0. And the negative binomial gives substantially higher probability for low counts and somewhat higher probability for high counts than Poisson. And there are all kinds of interesting versions of this that are very practically useful. Zero-inflated negative binomial, you can add that kind of two-class thinking to the negative binomial as well and fit even better. And zero-truncated negative binomial. Zero-truncated means that, for instance, a typical example is a length of hospital stays in days. So a person who's in the hospital will not stay 0 days, but it will start at 1. So it's truncated. You truncate away the 0. So you need a special binomial for that. And there's also a so-called hurdle model, and we will also refer to as a two-part model, where you have a model that's describing the probability of being in the 0 class, and for those who have some activity, you will actually describe the activity by the zero-truncated negative binomial. So it's 2 parts to it. We'll think of that when we come back to two-part modeling in March. We'll talk about two-part growth modeling. If you want to know more about this and have an example of various count regression activities, we have a web talk on our website. It's recorded in Camtasia. That is, you see a screen, a PowerPoint screen. You see me trying to point and me trying to talk and describe it. We have a work-through example that is fitted by various counts of count models, taking from a book that I'll refer to in a second. But just to tell you how Mplus handles this, you have all of these kinds of strange dependent variables. Binary and order polynomials referred to as categorical. Put a variable on the categorical list. Unordered polynomials nominal, put it on the nominal list. Censored, normal. Censored from below is YB. Censored from above is YA. Right now, we cannot handle the case where you have censored both from below and above. Count is what we just talked about. Poisson, U or U with P in parentheses, the same thing. Zero-inflated Poisson, U with I inflated, or U with PI, Poisson inflated. Negative binomial is UNB. Zero-inflated negative binomial, UNBI. Zero-truncated negative binomial, NBT. Negative binomial hurdle, UNBH. So that exhausts it. And for some of these models, you have no residual variance parameter. That's true for categorical nominal. But for censored, you do. For count, you don't. And finally, then, I believe, some good references. Again, Scott Long's book that I mentioned before covers this very well. Here's the classic Madala text that I mentioned, Madala. Here's the James Tobin refrigerator type of thing. Consumption of durable goods. Here's a classic article on Zip. And here's a new stat book in the first edition. I'm sure it'll come out with a second edition soon. That's Joseph Hilby, or Hilbert. I don't know where he comes from. There. How are we doing, Linda?
Okay.
You don't sound convinced.
No. I'm going to give you this, and you can make a judgment. Okay. So anyway, let me get started here. And first of all, I think we need to take a moment to figure out where we are. What have we just done this morning so far? Because if you want to think about yesterday, we started out looking at linear regression. And then everything we did was linear regression. Now today, we've started out looking at a lot of other kinds of regressions. And as I said yesterday at the beginning, the Mplus modeling framework is a set of regression equations of various types that are estimated simultaneously. So, we had the linear regression coefficient yesterday. Now today we've had probit, logistic. We've had the count, different coefficients for count, multinomial logistic regression, and different regressions for censored. And so all of those can be building blocks in the Mplus modeling framework. So you could have a set of equations, probit, logit, linear, count, multinomial logistic, and you could estimate all those simultaneously if that's what the variables in your model require. So if you had various types of dependent variables on different scales. So just to remind us where we are, and then after we went through linear regression yesterday, we went to path analysis. And that's what we're going to do today now. So we're going to look at path analysis in a situation where we don't just have linear regressions, but where we can have some of the other types of regressions we've just been talking about represented. So let's take a look at this, at this model. So here's a situation where the dependent variable is high school dropout. So it's a binary variable. Either drop out of high school or you don't. And you could consider, and we have a set of background variables, gender, mother's education, home resources, I think the expectations of going to college, lunch, which is a proxy for poverty, et cetera. So we have a large set of covariates, and we could consider doing a logistic regression. And that's a legitimate approach, and we could see the relationship between dropping out of high school and all of these different covariates. We could also consider doing a path model where we notice that we have math achievement measured in 7th grade and 10th grade, and it might make sense to actually pull that out and look at it more temporally. So Math 10 happens after Math 7, so we could instead look at a path model. And when we do that, what do we have? Well, Math 10 is a continuous variable. So we have linear regression when we regress Math 10 on this set of covariates. And we have a logistic regression when we regress high school dropout on this set of covariates. Logistic regression if we're using maximum likelihood. It would be probit if we use the default of Mplus. And we also have a regressing high school dropout on Math 10. So that's also another part of the same logistic regression. So we can do that, and there's another benefit to pulling Math 10 out. It just so happens there's a lot of missing data on Math 10. And so by pulling out Math 10, it's not a covariate, therefore missing data theory can apply to it. So missing data theory applies to dependent variables in the model. The model is estimated conditioned on the covariates, so if a person has a missing value on one or more covariates, they're going to be eliminated from the analysis. So when you pull Math 10 out and make it a dependent variable, in this case a mediator, then missing data theory applies to that. And also missing data theory doesn't apply when you only have one dependent variable. So by making a path model like this, you are not losing people with missing values on your covariate Math 10, as you would in logistic regression. Okay. So let's take a look at the input for Mplus. So something new we learned today is categorical option. So we have to say categorical equals high school dropout. If you don't say anything about the scale of a dependent variable, it's assumed to be continuous. And we're saying estimator equals ML. We learned earlier that the default in Mplus is probit regression with weighted least squares. So here we're saying we want logistic regression with maximum likelihood. Integration equals Monte Carlo is needed because we have missing data on the mediator. That's related to the use of numerical integration in estimating this model. That's a topic that is discussed in Chapter 13, slightly, but we're not going to go over here today. So, but most importantly, we have our model command. So we just translate high school dropout on this whole set of variables, female, everything, and then also math 10, because that's also a covariate for high school dropout. Math 10 is regressed on only the set of variables in the box to the left. So math 10 on. So high school dropout is going to be a logistic regression. Math 10 is going to be a linear regression. The type of regression depending on the scale of the dependent variable. Now here are our missing data patterns. We have two. So we have one pattern where nobody has missing on anything. And then the second pattern is missing on math 10 only. So for pattern 2, there are 574 observations. So if we did the model on the left, these 574 observations would be eliminated from the analysis because of missing data. And now we have our results. Because we're using maximum likelihood and numerical integration is required for this model to be estimated, you'll see that we don't get the type of model fit that you expect. You're not going to see the normal chi-square test statistic. You'll see, well, we'll see what we see on this next page, but you're going to see the log likelihood and various other types of information criteria, the AIC, BIC, sample size adjusted BIC, and well, that's okay, and that's all. And the reason that we don't give the traditional chi-square and chi-square related statistics like RMSEA and CFI and TLI is because when these are available only when means, variances, and covariances are sufficient statistics for estimating the model, where your input data could just be means, variances, and covariances, or just variances and covariances. But here, raw data are required. So these traditional statistics aren't available. What is done in situations like this is people usually compare nested models using what Bengt talked about yesterday, the fact that minus 2 times the log likelihood difference is distributed as chi-square for nested models. So here we are, high school dropout on. So we know that in the estimate column, these are logis or logistic regression coefficients. We have standard errors for them and the ratio of the estimate to the standard error, which we look at as a z-score. So we can see values that are larger than plus or minus 1.96 are going to be significant. And you can see that there are several. For example, mother's education is significant. And then we want to also look at the sign negative. So as mother's education increases, the probability of dropping out of high school decreases. So this is just like we talked about before. There's nothing special in the interpretation. Here's another one. A positive dropout thoughts in the 7th grade is also significant positive. So as dropout thoughts in the 7th grade increased, the probability of dropping out of high school increased. So here we're not talking about values, but probabilities. And then our second regression, math 10 on the set of covariates, math 10 being a continuous variable. These are linear regression coefficients. So and here mother's education is not significant, home resources is. As home resources increase, the scores on math 10 increase. So nothing really special about that. And in the rest of the output, we see the intercept, that we have an intercept estimated for the continuous variable, a threshold for the categorical variable, no residual variance for the categorical variable. That's not a parameter that's estimated, but a residual variance for math 10, which is significant, which would say that there are many more possible covariates for explaining the variability in Math 10. And we have our observed variable R squares. And as Bengt mentioned, the R square for high school dropout is really based on the latent response variable underlying the observed binary variable high school dropout. And you might want to think of that as a quasi R square. And then the R square for Math 10, which is fairly decent. Let's see, I think I'm going to go over here for this.
I would skip that.
You would skip that? Okay. Okay, I have to say one word about it.
Yeah, do.
Okay, we're going to skip this next example, but just to say what the point is that with that probit and logit regression differ when there are mediating variables. So S is regressed on E, which is regressed on V. So E is a mediating. It's in the middle. So is F. S on F and X. Okay. So anyway, so in logistic regression, when a variable is a mediating variable, it's in its role as a covariate. So in its role as a covariate in relationship to E, or F as a covariate in relationship to X. With logistic regression, these are treated as the observed variable. But with probit regression, these are treated as the underlying latent response variables. And this is in their role as covariates. So that's a distinction that you should know.
I just want to point out that you don't have to scribble it down, but on slide 83 you have this text explicating that a little bit further.
Okay, that's all I had to say.
Good. So we're running a little bit short of time for where we want to be for lunch. So I'm going to make the decision that we're going to skip some of the material coming up here. I'm not going to talk about this slide 84. I'm going to skip these slides, 87, 88, and instead go to 89, which I think is an important topic in itself. So we'll start on slide 90. So Linda made the transition to multivariate response. So I talked about one single dependent variable in all of what I talked about. So regular regression, one dependent variable. Then Linda introduced path analysis, which had two dependent variables, one continuous and one dichotomous. Now we're going to go to many dependent variables. And we're not necessarily focusing on regression, but we are more going to be like where we were yesterday before lunch, namely talking about factor analysis for the first time. So we're going to take a look at something that's called item response theory. It also has the name latent trait modeling, or equivalently factor analysis with categorical outcomes. All three are one and the same. And the idea is that you have, say, dichotomous variables, U1 through U5 in this case, or ordered categorical, and you have a continuous or several continuous latent variables, in this case denoted eta. So the first thing we note then that the scale type for the observed and for the latent do not have to be the same. So you can have a continuous latent variable and binary observed variables. That's perfectly fine. In fact, you can have continuous observed and a categorical latent, and that's fine as well. And that will be called latent profile analysis, a type of latent class analysis when we talk about topic 5 a year from now. And the idea is that this picture then can be interpreted like this. On the y-axis, you have the probability of an item assuming the score or the category 1, say scoring, getting the item right in educational achievement testing, as a function of, say, the ability of the student And these 5 items are 5 different kinds of tasks. And the probability curves are these S-shaped curves, probit or loaded curves, saying with different slopes. So this item has a little bit lower slope than this item, the 2 leftmost curves, saying that as the ability increases, the probability of getting the leftmost item right increases more slowly than the second rightmost item. And the slope differences, well, we'll get to that in a second. Now, IRT, as it says on slide 91, typically does not use the full structural equation model that we talked about yesterday, but a subset of it. But if you look at equation 127, you will see the so-called measurement model of the structural equation model, relating the observed variables to the latent variables eta. In this case, the observed variables are shown as U star variables. That is, we use the latent response variable formulation. But that's not essential. And then equation 128 gives the structural part of the model, relating the factors, the latent variables, continuous latent variables, to each other and to background variables. So what I'm saying is the IRT typically does not use what's in parentheses in equations 127 and 128. So typically there are no x variables involved. And in fact, typically you only consider a single factor as in the picture on slide slide 90. So there's a lot of work in this area in item response theory developed by educationally oriented psychometricians. Key names here, Darryl Bach, Bob Gibbons, and E.G. Meraki. And the aim, they have a little different nomenclature for this. Item parameter estimation by maximum likelihood is called calibration. Estimation of factor scores, eta values, is called scoring. And instead of a factor determinacy to describe the quality of the estimated factor scores, you have so-called information functions. I'll talk about it in a second. And you have test equating, which has to do with the quality of measurement parameters, quality of measurement parameters across groups. And you have diff analysis concerns, which has to do with those direct effects that we talked about yesterday. Now, in Mplus, you have the 2 estimators, maximum likelihood and weighted least squares, for these kinds of categorical response models. And with ML, which is a full information estimation, sometimes called FIML, we offer both loaded and probit modeling. With weighted least squares, we only offer probit modeling. Now in IRT, the continuous latent variable is called theta, which is a little confusing when you come from our notation, where theta is the residual variance. So theta, their theta is our eta. And the logistic model that we talked about, they call a 2-parameter logistic IRT, or 2PL, the 2-parameter logistic, 2PL. And they write it somewhat differently. If you look at the loaded part in the logistic formulation, you have a constant d times a parenthesis theta minus b, where theta is, again, the eta, or factor value. And they have a constant here, 1.7. It's actually a very close cousin to 1.81, square root of pi squared divided by 3. This is to make A and B, the coefficients close to those of probit. We're using logistic, but to make the probit loaded differences smaller. 1.7, there are some arguments for 1.7 being better than 1.81. I won't go into those. It's amazing. People have written papers about that. But I guess it's useful. So A is called discrimination and B difficulty. As we will see, A has to do with our factor loadings, and B has to do with our thresholds or intercepts. So discrimination has to do with the steepness of these curves on slide 90. The steepness, how quickly they react to an eta change. And difficulty has to do with the locations, right-left location of these curves on the eta scale. The two-parameter normal ogive IRT, the normal distribution, the probit version is called the normal ogive or ogive. People use different kinds of pronunciations. And it uses the normal distribution function again. And typically, theta, as it says at the bottom of page 93, theta is standardized to 0 mean and unit variance. So not setting the metric by the first loading fixed at 1, but fixing the variance to 1 instead. And in fact, Mplus now offers a translation of our factor analytically oriented parameter estimates to the IRT parameters. And you can look at that relationship on slide 94. And you see the conversions here at the bottom of slide 94. Automatically done in Mplus. I will not go through that. There is a technical appendix which describes this. On the Mplus website, we have a section called Technical Appendices that have various pieces to it. And you will easily find the technical appendix relating to IRT, which is getting to be a more and more popular reason to use Mplus because the IRT modeling is so general in Mplus, handling multi-level IRT and mixture latent class IRT and latent class multi-level IRT with all kinds of twists and turns. And again, now we talk, in terms of talking about factor analysis, as in this picture, the fact that you're trying to measure a continuous latent variable doesn't stop you from having all kinds of response variables, just like we talked about in the regression. They can be binary, ordinal, nominal, count, continuous, and any combination of those kinds of variables. So if you have a measurement instrument with a combination or mixture of response variable types, you can easily plug that in and do this kind of IRT or factor analysis model. And the advantage of Mplus is that it's very easy to go towards the full SEM model on slide 91, equations 127, 128, with multiple factors and with covariates. And after lunch, Linda's going to show you an example of a mimic version of this for binary outcomes. Testing the model against data, just finally, you can use model test in terms of frequency tables, the Pearson chi-square, and the corresponding likelihood ratio chi-square for the frequency table. But typically, that becomes useless. When you have many variables, you will have so many zero cells that these approximations do not work. And therefore, at the bottom of slide 95, we point out that you can look at fit to more collapsed tables, particularly bivariate, all the bivariate tables that follow from the multivariate frequency table. And you do that by Tech 10 output. So I'll stop there, and I think it's time to take questions before the lunch break.
Yes.
On slide 69, where we're talking about the ZEP, in instances where their frequency, but there have been categorized into ordinal variables such as 0, 1 to 2 instances, 3 to 5 instances, 6 to 10, etc. Can ZIP be used in those cases as well?
So the question is about using Alameda scoring, right?
Yeah.
So categorized counts, I would not use the Poisson. I would not use the count approaches for categorized counts, but I would use instead the ordered polynomous approach for that.
Okay. The problem is that there's the preponderance of zeros, though.
But that doesn't hurt. The preponderance of zeros does not hurt. I'm glad you asked that. It does not hurt the assumptions of the ordered polynomous regression.
Okay.
There you can have as many people as you want at the zero category. There's nothing wrong with that.
Okay.
Although you don't get the benefit of thinking in terms of two classes that, say, zip has.
Okay.
So if you want to combine the idea of two classes and order polynomous regression, you have to do a little methods dissertation on it. We think it's possible, but it hasn't been explored that widely as far as I understand.
But we're going to talk this afternoon a little bit about when to treat variables as categorical. So I think that we'll go over that a little bit.
Gentleman in the middle.
On slide number 60, you talk about the data.
Slide 60.
For multinomial logistic regression, how should the data be in Mplus? Can it be, does it have to be at individual level, or can it be aggregated?
In Mplus, well, you can have frequency data, and like I showed earlier with the coal miners example, but generally the variable would be in a single column, and a person would have a value of 1, 2, 3, or 4, depending on which category they're in.
But you can have like coal miners data here also,
Right.
giving the weight as another value.
Yes.
Okay.
Okay, yes.
I have two questions. The first question is about slide 16.
Slide 16?
16.
60? The one we have here.
Okay.
I wonder if we can get the proportional of logistic regression based on the multinomial logistic regression by restricting the data, the parameter of data for different categories to be the same across the categories.
Okay, so here's a method question. This person wants to use the multinomial unordered logistic regression and put constraints on the parameters equal slopes to get the ordinal. So I think that may be possible. I haven't tried that, but it should be possible using model constraints.
So you would just label the parameters and then in model constraint, hold them equal.
But-
Oh, actually, you could just do that using the equalities. You don't need model constraint.
Mm.
So if the only thing you want to do is hold parameters equal, you can do that in the model command. For example, in the model command, we have a shorthand u on x1-x3. That can be expanded to say u1 on x1, u2 on x1, u3 on x1. And if you put a parentheses 1 behind each of these, they would be held equal during model estimation.
But it has to be explored. I haven't done it, so I don't know what kind of pitfalls there are embedded there.
Okay. My second question is about the slide 76.
76?
I wonder why the data with missing on map 10 will be dropped from the analysis. I know there is a default for Mplus version 5. That type is missing is the default. And map 10 is not the independent variable, so it will be dropped from the model.
Can you repeat that, Benny?
Yeah, so the question is about Linda's slide 76 here. We have a missing data pattern for, we have missingness for math 10 for 574 individuals. And Linda was saying that if we have the model on the left here, it's a covariate, and the default in Mplus is to delete individuals with missing on any covariates. But when we consider the model on the right, math 10 is a dependent variable, and therefore the missing data theory that we deal with in topic 4 kicks in, and you don't have to delete people.
Unclear now. So it's included in the path model,
Yeah.
but deleted from the logistic regression model.
Exactly. And the interesting thing is that the missingness on math 10 is selective. We have more missingness on math 10 for those who drop out. So it's a missingness that you really want to deal with carefully. And here the idea is that the background variables predict the missingness, and you fall under the so-called MAR assumption. Very exciting missing data theory treated in topic number 4. Okay, I think how many more questions do we have time for? Because we have to be back at 1 o'clock.
Right, we're going to be back at 1, so we'll take as many questions as you want to ask. So let's take
But
a
it
couple
shortens
more.
your lunch, so there's a
All right. So,
balancing.
okay. And for those of you who want to leave, just please.
Yeah.
Slide number 91.
Okay.
This gentleman already had a question,
I see.
so we
Okay,
have to
let's-
spread it out. I'm sorry. Okay, he wants it. Slide number 91. Okay, here it is. Yes. Is there a typo? What is the typo?
I mean, after parenthesis, the last line doesn't make sense. The start of the parenthesis.
Yeah, no, so this lambda eta plus kappa times x plus epsilon. I think that's right. Okay, another question. Gentleman in yellow in the back.
Yes, slide 90.
Slide 90. So here it's really a choice between statistics and eating. And it's a sort of a 50-50 vote here. Can you speak up?
Okay. You discussed item response theory as a factor analysis of the categorical outcome. Is
Right.
it? But your diagram has only a model for one factor. So should we be doing this one factor at a time, or should we do this?
No. In Mplus, you can analyze several factors at a time. And in fact, we're going to show you exploratory factor analysis. So there's no restriction on the number of factors. I'm only showing one factor for, in this case, because in IRT, you typically only work with one factor.
And we looked at models with more than one factor yesterday, didn't we?
Yeah, but not for categorical.
Right, but
But
still.
that's allowed here too. Yes, gentleman in the back.
Yeah, on slide 75,
75.
when you're doing the path analysis with binary outcomes, can you estimate the indirect effects with either IND or VIA the same way you do for continuous? And then I guess more specifically, can you do that when you're then dealing with missing data with the integration command?
Yes.
So the question is, can you do the indirect effect from background variables via Math 10 to high school dropout? And the answer is yes. And there's even a paper on our website about doing indirect effect estimation with a binary dependent variable. It's by McKinnon and Brown, Hendricks Brown. Clinical trials paper. Yes.
Do you have special considerations when you have lots of zeros in the independent variables?
I don't want to,
So what about having a piling up of zeros in the independent variables? No, I would say no, because it's just you just condition on those variables. You're just talking about values, a linear effect of that variable. It would only have a concern if linearity doesn't hold for that kind of scoring, linearity in the influence of x on y, but it would not alter our other modeling concerns. Yeah, would not. Okay.
Okay. One more question? Okay, of course.
And it's actually on slide 84, which you didn't go over. But using the theta parameterization, if Math 10 were was an actual binary variable, then we would have to use theta parameterization versus delta, correct?
Here's the rule. Theta
has to be-
needed for models where categorical outcomes are predicted by categorical dependent variables while predicting others. So the answer would be no.
The chain has to be longer than 3 for that. And, right, so, and we'll tell you if you need to use it. I would always recommend using delta and only using theta in that situation. And if you're in that situation and you try to use delta, we'll tell you.
Mplus will tell you
exactly.
that you need. And we'll talk a little bit more about delta and theta in the afternoon.
All right, we have another question?
Yes, page 69.
69?
Yes. How do we calculate the variance and mean in Mplus?
How do you calculate the values?
Variance and mean in Mplus.
We do not give explicit estimates of these quantities, but you can derive them from the probability from the parameters that are estimated using model constraints. So you have to take the probability of being in zero class and do this and get lambda from this expression rather, but you would have to do that yourself.
You know, it's, in order to use Poisson, it's variance equals mean that you mentioned, right?
Yeah.
So, but it's a zip variance greater than mean. So I just curious about calculating how do you know, it's
well, how you know which one you choose is by log likelihood difference testing. You do the Poisson model, and then you do the zip model, and you see which one is best in terms of log likelihood and maybe the Bayesian information criterion as well. Okay, with that, we have to eat.
Okay. Now here on the left screen is bivariate fit information that you also get from Tech 10. So for example, we have two variables here, property and shoplift. So they're binary, so they form a 2x2 table. So we have category 1 for property and category 1 for shoplift. That's one cell. Then category 1 and 2 is another cell, 2, 1, and 2, 2. So these are the proportions in the 4 cells of the frequency table for property and shoplift. So we have the model, the sample values and the model estimated values. You can see how close those are. And then we have a standardized residual related to them. And you can see that here none of these values are actually very large. So that would indicate that there isn't misfit for those two items. Here are different items. Less than, oh, Jackie? Okay.
Cross that out.
Yeah, cross this out. This was an accidental mistake, I guess, by...
Can you point to it again?
Yeah, right here. This shouldn't say property and shoplift. Apparently, the person who did this copied this whole thing from the prior slide, not realizing that the variable names were less than 50 and greater than 50. So cross that out. So the variables we're looking at here are less than 50. Oh, that's, I think, stealing less than 50 or greater than 50 in goods, $50. And then we have the 4 cells here for that 2x2 table. And now we see that we have a residual larger than the absolute value of 1.96. And we can take a look then at what cell that is. So that's less than 51, greater than 52. And when you have in a bivariate table large residuals, standardized residuals, it could mean that you might want to add a residual covariance between less than 50 and greater than 50 to improve model fit. And once again, though, you would want that to make some sense, that those residuals should be covaried. Okay. Actually, that's you. I was going to say, I didn't think that looked familiar.
Looked like me. And now we're going to entertain you with beautiful pictures straight out of Mplus plot option. But what do they mean? So, yeah, we'll show them like this. So on your left screen are the what's called item characteristic curves in the IRT language. So when IRT people say ICCs, this is what it means. The logistic distribution, the logistic regression shape that we've looked at many times today. It does not mean interclass correlations, but ICCs are the logistic curves, one for each of the different items, describing the probability of, well, you have the choice in your plot options in your menu, and this is the highest category that is endorsing the item, that is saying you do engage in that kind of property antisocial behavior. And you can see that these items are pretty homogeneous, certainly homogeneous in terms of their thresholds or what's called difficulty. They all tend to start going up drastically around the value of 1 or 2 on the F factor here on the x-axis, which sort of is a weakness of the measurement instrument. When you do achievement testing, at least, you would want to spread out the items to cover a wider range in their measurement of the factor. So you have both easy and hard items, so to speak. And likewise, you could talk about more or less extreme forms of antisocial behavior and thereby spread out these item characteristic curves a little bit here by them having different thresholds or intercepts. So that's a way to see if you have good measurements or not, and here I would say you don't. So whoever designed this instrument probably didn't think in terms of measuring a wide range of antisocial behavior, but only measuring very well in a small range. They may not even have thought about factor analysis, for all I know, much less latent class analysis, perhaps. So anyway, this is simply the logistic curve, probability U equals 1, which is the highest category, which we label as category 2, the lowest being category 1 for binary case. So what do we have on the right? Well, that's an interesting thing that IRT people look at. Test information is related to the precision with which we estimate our factor scores. Test information is related to the precision with which we estimate factor scores. And in fact, it is the inverse of the standard error of the estimated factor score. Now, for continuous items, we talked about precision of factor scores in terms of factor determinancy. But here, it's more typical to talk about information curves, that is, the inverted standard error. And a very special feature of that for categorical outcomes is that that standard error, or inverted standard error, varies as a function of the true factor value. It varies. So you have very, very low information in the tails, that is, high standard errors in the tails here, and lowest standard error around 1 and 2 again. Lowest standard error and therefore highest information about the factor score here. The fact that you have most information here in the middle is related to where these curves are located. That is, the extremeness of the items, positioning them around here makes for the information about the factor to be best, to be highest in that same range. So people who formulate achievement tests like SAT and ACT in Princeton and in somewhere in Iowa.
Iowa City.
Iowa City. Are you from Iowa City?
Yes.
And I knew that. I mean, I knew about Iowa City, but do you have anybody from Cincinnati? Yes. All right. Anybody's birthday today? I'm sorry, I'm getting into... I slipped into my lounge act. It happens all the time. Okay, so it's interesting. You can see in Iowa City and in Princeton, they're very concerned with having test information curves that have a wide enough tails, to measure well in a wide range of abilities, because not every student is sitting at 1.5 on the F scale. So they pay a lot of attention to it, and they write a lot of papers about this. They have whole journals devoted to this, like GEM, Journal of Educational Measurement, and APM, Applied Psychological Measurement, and they even spill into psychometrica. They're everywhere. But they do good statistical work, and it's useful. So it's very informative to look at the test information curve. So you can borrow that idea for if you wanted to analyze the DSM diagnostic criteria. There you go. And they probably are measuring well only at a very limited range as well. So several lessons here. First of all, compared to the continuous case, the test information curve is not constant. For the continuous case, the information, the standard error would be the same across all values of the true factor score. For continuous outcomes, it will be the same. That's not the case for categorical outcomes. That's number one. And we, again, repeating, test information curve is the inverted standard error. I can't remember if it's inverted standard error or inverted standard error squared. It doesn't matter. But it has to do with standard error of the estimated factor score. And very often you don't talk about the standard error for the estimated factor score. You just talk about the estimated factor score for an individual. But that's like giving only a point estimate, not a standard error. In fact, in current Mplus 5.21, we are neglectful and don't give the standard errors for the estimated factor scores. So we will do that in the next version. Anyway, so now you know a lot more about IRT output that you can get from Mplus. And let's look at one more thing here. When you talk about estimated factor scores, we mentioned yesterday that statisticians call that empirical base estimation. And we mentioned that it had to do with EAP, which is sort of a Darrell Bach, a psychometrician's acronym in his bilog program, expected a posteriori, versus the modal, which I can't remember what it's called now, but doesn't matter. So the idea is you can plot the estimated factor scores. You can do a histogram for the estimated factor scores. Estimated factor scores are obtained in the following way. You have a prior, and then you have data, and that gives you a posterior. And the posterior is for each individual, and you find the expected value in that posterior for the individual, and that gives that individual's factor score value. Prior, what is it? It is an assumed normal distribution of the factor, plus the data, which is the response patterns, the U outcomes that Linda talked about. And together with that, from the estimated model and the data, you get a posterior distribution for each individual. Calculating those, putting together all those estimates, here's the plot for the sample that we talked about for the antisocial behavior. And it also shows, in a sense, that we're measuring rather poorly, in the sense that there are a lot of people piling up here with no problem. If we had formulated items that were in IRT language a little easier, a little less extreme antisocial behavior, we would be able to tell these people apart and have a softer declining tail out there. Okay, further readings on IRT. There are lots of them. I used to teach from Hamilton and Swaminathan's 1985 book at UCLA. It's a pretty good book, although it's now a little dated. A later one is Baker and Kim, quite technically oriented. Darrell Bach has contributed lots of papers, and those papers, here's the history of IRT. Those papers are nicely collected in a book from Scientific Software, the company that distributes these IRT-related programs, and also Lisrel. And it's compiled by Matilda Dutoy. Emerson and Steve Rice, I can remember, has done an applied IRT book. And here is an applied paper in GEM that I wrote some time ago, talking about instructional sensitivity mathematics achievement test items that is taking into account not only how well students answer, but also how much opportunity they had to learn the specific topic. So having item-specific opportunity to learn information in your model is kind of a nifty type of situation. And here's the, we have various web notes on the Mplus websites. So not quite papers and a little bit more than just the tech documentation. Here's one that really should be published one day. Multiple group and growth modeling in Mplus, talking about how to deal with categorical variable modeling. So when we go through very quickly parameterizations in weighted least squares called theta and delta parameterizations. Here's the technical paper that explains what that is. Here is a good paper in Psychometrica on the relationship between item response theory and factor analysis of discretized or categorical variables by Yoshio Takane and Jan DeLeo. And by that, Linda, should we have a question and answer session?
No, we have 2:30.
2:30, okay.
Wait, isn't it 1:30? Yes. Yeah.
Oh, I misread. I thought we were at ESEM here, and I got so excited. It's exploratory factor analysis, so I'm an hour away.
That's your reward.
Yeah, all right, thank you. And I'm sure you mean that in the best possible way.
I do.
Yeah. I'm sorry, what?
We're at exploratory factor analysis.
Oh, this.
Slide 113.
113, yeah, this is 114. So just to clarify, we are here on 113, exploratory factor analysis. And we now want to generalize our thinking beyond the one-factor case that is so prominent in item response theory. And we want to first go through the EFA and then maybe the CFA following that. We'll see. So on slide 114, left screen, we're talking about outcomes that could be categorical, censored, or counts. So anything that's not the regular continuous outcomes that we talked about yesterday. Since we do EFA, we have the issue of M-square indeterminacies, a potential problem that we turn into a potential opportunity, namely a flexibility to learn by exploration about our data through the rotations that we talked about, the orthogonal and the oblique rotations. And they are carried out by the same techniques as with continuous outcomes once you have obtained the factor loading matrix. Now, with these kinds of outcomes, categorical, censored, and counts, maximum likelihood estimation is typically a little bit harder than it is for continuous outcomes. In fact, it's computationally feasible for only a few factors. And the reason is that the combination of categorical, censored, and counts, I'll call them non-normal outcomes, if you know what I mean. Not non-normal continuous, but non-normal, really non-normal. That combination of non-normal outcomes and continuous latent variables in maximum likelihood analysis is a very tricky combination from a numerical analysis point of view. If the estimator is maximum likelihood, the algorithm, the best algorithm for dealing with this is some form of the so-called EM optimization algorithm. EM stands for expectation maximization. Later on, like topic 5, we actually say what EM is in more detail. But in the EM algorithm, we need to be able to do certain computations that involve integrals. And you remember the integrals maybe from, maybe not high school math as much, well, high school math too. But what they didn't tell you is that we don't have these closed form expressions very often for integrals, but integrals have to be handled by numerical analysis through so-called numerical integration, and that can be time consuming. Numerical integration is the reason why we can only work with a few factors. Numerical integration, where the heaviness of the numerical integration increases as the number of factors increases. The heaviness computationally also increases as a function of the sample size. We talk about numerical integration and tips for doing that well in later topics. Maximum likelihood estimation also has the problem of an overall test of model fit, because what we want to do is work with a frequency table for many variables. As Linda said, you have many cells. Excuse me. And many of those cells have zero frequency or low expected values by the model, and the chi-square distribution is not well approximated. Chi-square testing breaks down. So those are some problems with maximum likelihood estimation. We have then, therefore, the alternative limited information weighted least squares estimation. Limited information means that we only use information from univariate and bivariate tables. Univariate and bivariate. Not trivariate, not four-variate, not p-variate, not higher order moments like that, but only univariate and bivariate. And then we use a weighted least square estimation technique, similar to wall testing, in fact, that we have a technical description of at the very end of today's handout. And it means that the estimation becomes computationally feasible for many factors, whereas it was only feasible for a few factors for maximum likelihood. But you cannot have a huge number of items, whereas maximum likelihood works well with many items. So you can sort of use these two techniques in tandem, complementing each other, except you have no good approach when you have many factors and many items. There we're stumped at present, but we are still working on it. What you do here in limited information is you're able to test the model against the information in the bivariate tables. And you're going to see that we're going to get a chi-square test of model fit and the CFI and all of the RMSEA things that we're used to from continuous variables, which may be some comfort for you by using weighted least squares. Now, there's a discussion about the underlying assumptions behind weighted least squares in ML, and it's particularly relevant for the topic that we're moving towards, and I think Linda will cover, namely analyzing correlations for these U star variables, the assumed underlying continuous variables, U stars. Correlations among the U stars are given these funny names: tetrachoric, polychoric, polyserial. So a U star with a binary observed counterpart is called tetrachoric. Ordered polynomous U star, ordered polynomous pair of U's, the correlation coefficients for the U stars is called polychoric. If one of the U stars is continuously measured and the other polynomously measured, you have a polyserial correlation. And these are correlations for underlying U stars. And those are the correlations to which we fit the model parameters when we work with weighted least squares. So that then leads to a controversy, because some people say, what are those correlations? We don't believe in U stars. And we have to have the assumption of multivariate normal U stars, and who knows if they're multivariate normal. Therefore, we added this slide to remind people that when assuming normal factors and using a probit link, ML uses exactly the same model assumptions as weighted least squares. This is because the combination of normal factors and probit links results in a multivariate normal U star variable, set of variables. So if you in IRT, and when I say ML, I'm mostly thinking of the IRT context. So in IRT, we assume normal factors and say probit link, which is a normal ogive or ogive model. That implies multivariate normal U star. So that is the same as the assumption that we make in WLS, normal U stars, for which the tetrachoric, polychoric, and polyserial correlations are relevant. These are then second-order statistics using second-order moment information, which is what WLS works with, whereas ML uses full information from all moments. So there's actually very little difference between ML and WLS. No difference if you assume a probit link, and pretty much the same even with loaded link. So that's a defense of the underlying U-star correlations. And in fact, when ML and weighted least squares have been compared in the literature, and I will show you some references to that effect, imperceptible differences are found. Here's the latent response variable formulation if you want to draw a picture like this in a more elaborate fashion. You actually picture the latent response variables here as underlying the observed variables where the relationship is a threshold relationship. If it's binary U1, say, then when U star 1, U1 star is greater than tau 1, the threshold tau 1, then we observe U1 equals 1 instead of 0. And so all of these are continuous and continuous multivariate normal, so that the bottom part here, from here on down, from the U star down to F, is a standard continuous indicator, a linear regression factor analysis. The only difference being that these variables are not observed. Minor detail. That's what multivariate statistics takes care of. So this is just an alternative way of drawing it and drawing your attention to the fact that one can analyze these loadings, for instance, by knowing the correlations among these variables, these tetrachoric, polychoric, and polyserial correlations. And that's what weighted least square does. Still me?
Yeah.
Right.
All the way through the ESEM.
Now, you can look at this in a more general fashion, going from the binary to the ordered polynomous case. And here's a picture. We start with what we observe. U for a variable, here's variable I and variable j, two variables. And say that you have 1, 2, 3, 4, 5. It could be a Likert scale or a Likert scale, depending on where you come from. And you see that it's fairly skewed, piling up at the high point here, piling up at the high point here too. This kind of observed variable situation can arise from U star variables, U star I, U star j, that could be bivariate normal, positively correlated, with thresholds that are positioned here, the lines, 1, 2, 3, 4 thresholds for UI, and 1, 2, 3, 4 thresholds for UJ. And could be perfectly bivariate normal, but due to the fact that the thresholds are asymmetrically positioned across the range of the U star variables, we will get this skewness. So this situation could be an illustration of your measurement item formulation not capturing the full range of the U star variable, like a less extreme antisocial behavior, whatever that might be, could be represented, or a response scale from strongly disagree to strongly agree that's modified somehow. So again, this would be a polychoric correlation that could be calculated for the U star relationship, polychoric correlation between those underlying U star variables. Now, slide 118, just to go through in detail the types of U star correlations with underlying normality. Both use dichotomous, tetrachoric, both polynomous, polychoric, one dichotomous, one continuous. This is a biserial and a polyserial. Here is the beginning of a long technical story, which we will give you references for. But essentially, it says that this underlying normality assumption that we talked about can be relaxed when you have X variables, covariates, present. And the underlying normality that instead becomes an underlying normality for the residuals. So underlying conditional normality given the x variables is a more flexible, less stringent assumption. And if you're interested in that, I have a 1984 psychometric article on that aspect I will point you to later on. So now we do an EFA of these items. And you have the slide 119 talking about the variables property through gambling. That is looking at all of the items, property, all the way through here in the names equal list to gambling. And the rest of the variables are background variables, or actually DSM variables too. I forget what it's DSM for. I don't think it's gambling, but it's something else. And they are categorical variables. And we just say the same thing as we did for the continuous EFA. EFA with extracting 1 through 5 factors. Whereas the only difference is to really saying categorical equal here to get into a probit logit situation. And since we say nothing about the estimator, the default is the simpler weighted least squares estimation. Simpler at least when you have many factors like 5 here. And you look at the eigenvalue plot, and then what you get is an eigenvalue plot for tetrachoric correlations, the U-star correlations. You draw a line along the scree here, the rubble at the bottom of the hill. And whatever sticks up above that rubble tells you how many factors it should be. 1, 2, 3, 4 perhaps, although it's not easy to tell in many situations. So you have to test like 3, 4, and 5, or look at 3, 4, and 5. Here's 3 and 4 factors. We have a very large sample and a very high chi-squared to degrees of freedom situation. Actually, in this case, all you should pay attention to the p-value. P-value clearly rejects the model, but let's take a look at our more friendly measures. CFI, an excellent CFI, an excellent RMSEA, and an excellent standardized root mean square residual, both below 0.05. So this is a model that seems to be quite useful as an approximation to the data. Again, we cannot expect well-fitting models for data that have been put together without the idea of measuring distinct factors, but probably been put together by committee, although I may be too negative about that. Here you see the rotated loading matrix. If you look on the left screen on slide 123, it says quartimin, which had about a half year's survival as our default. We went from Promax to a brief stint of quartimin, and now it's geomin. Quartimin developed by Bob Jenrick. He was our consultant on the ESEM, and he agreed eventually on geomin being a little bit better. But it doesn't matter. It's probably fairly similar results here. So the bolded values are guiding your interpretation. First factoring having to do with property, shoplift, and stealing less than or greater than $50, and taking an auto and breaking into a building. So that's clearly a factor 1 is property offense. Factor 2, fighting, threatening, injuring, has to do with person offense. Factor 3, smoking pot, dealing in drugs, or using other drugs, selling drugs, etc., having to do with drug offense. And then you have the factor correlations here. So all of the stuff here is interpreted in the same way as we did yesterday for the EFA for continuous outcomes. And we can get significance of the rotated loadings here as well. I don't remember why we haven't included them here. Now, if you go to 4 factors, CFI is still very good, and the RMSEA and SRMR are very good. So we can't distinguish statistically between them. So let's do it in terms of interpretations. Can we support 4 factors? Is the 4th factor interpretable? And here you have the loading matrix for 4 factors. First factor seems to still be the property offense factor. Excuse me. And second factor, the person offense. Third factor, the drug factor. And the 4th factor, where is it? It has a considerable loading only on selling drugs and nothing over here except a little bit of gambling. And no other loading is very large. Here we have a situation where we have at most 2 indicators for the factor. So whatever that factor 4 is, it is poorly measured by this measurement instrument. So if you think there is something important that's picked up by selling drugs and gambling, well, then you should create more items that could possibly cover those items. And using force, where's that? Oh, yeah, using force. Yeah, OK. 0.491. So that could be. It actually makes perfect sense. It makes sense. So what is the factor? Guns, drugs, and rock and roll. No,
Organized crime. Oh my God, the mafia.
Oh, it's a mafia factor. And
now, but see, I think we didn't highlight that one. Well, I guess we.
The whole room starts shaking when we talk about that. Well, it's okay. So you discovered something new. Congratulations.
Okay. So now we're going to move on to practical issues regarding when to treat these categorical variables as when you might consider treating them as continuous and not having to use categorical variable methodology. Because I'm sure all of you have heard people say, well, if you have 5 or more categories, you should just treat the variable as a continuous variable. And actually, it's less dependent. When a variable is best treated as categorical, is less dependent on the number of categories than the presence of floor and ceiling effects. And we're going to take a look at a couple examples of that. And also, even if you could treat the variable as categorical, as continuous, if you're really interested in estimating probabilities or odds and presenting your results in that way, and you have categorical data, then you might want to use the categorical data methodology, even though the variable could be treated as continuous without attenuating the correlations. Because that's what happens when you treat a categorical variable as continuous. The correlations are attenuated, particularly when there are floor and ceiling effects. And we're going to see what we mean by floor and ceiling effects. So when you then treat the variables as continuous, it can lead to factors that just reflect item difficulty. For example, you can have a factor where all the easy items load and a factor that just has all the difficult items. So it has nothing to do with the essence of the items, but just the item difficulty. And sometimes when you treat categorical variables as continuous, as we saw this morning, the predicted probabilities can go outside of the range of 0 to 1. So we're going to look at 2 situations. Okay, so over here on the left screen, we see a situation where if you treated this variable as continuous, you would get correct parameter estimates, but incorrect standard errors and chi-square. So, and on this right screen, this is what would be referred to as a floor effect. So when there's a piling up at the lower end, it's a floor effect. If there were a piling up at the higher end, it would be a ceiling effect. And you might say the variable is skewed, but usually skew refers to a continuous variable. So if you have variables over here, you're going to not only get incorrect standard errors and chi-square values, but you're also going to get incorrect parameter estimates. So even if you have a variable that has 5, 6, 7, 8, whatever number of categories, if you have the piling up, if you have the floor effect or the ceiling effect, then you really should treat the variable as categorical. You're not going to even get correct standard errors, chi-square, or even parameter estimates in that case. So that's how you make the decision. Now, here on the left screen, you can either transform the variable and treat it as continuous. We don't usually do transformations, but sometimes people do that. Or you can treat it as a continuous variable and use the non-normality robust maximum likelihood estimation. So you can use an estimator that's going to take the non-normality into account. But such an estimator does not help you if you have a situation like on the right screen. Then you really need to take into account that the variable is categorical and use the correct methodology. And note that this came up, I think, before lunch. A piling up of at one end or the other end doesn't mean that you should treat it as a count variable. It isn't a count variable, it's a categorical variable, and the methodology has been developed to take those situations into account. So categorical variable methodology doesn't assume that anything about the distribution of the observations across the categories. Okay, now Bengt actually went over this and pointed out that even that though you have very skewed observed variables, you might still have meet the assumption of multivariate normality. So I won't go over that slide again. Now here's the situation on this slide. So to see what happens and why Pearson product moment correlations are really unsuited to categorical variables in some situations. So let's take an example where we have two variables, U1 and U2, categorical. The probability of U1 equals 1 is 0.5 for U1, or the proportion that answer 1 is 0.5 for U1, and 0.2 for U2. Now in this situation, you get a maximum Pearson correlation of 0.5. So if you look down here, you can see here's the 0.2 for U2, here's the 0.5 for U1. Now these are marginal probabilities. Now here in these cells we have 30, 20 is 50, 0, 20 is 20. Now there's no way that you can rearrange the numbers in these cells that you are going to ever get a Pearson correlation greater than 0.5. Although a tetrachoric correlation of that same information would be able to go larger than 0.5. And so therefore, you have a restriction of range on the possible estimated correlation, and that's never a good situation because the correlation should not depend on these marginal values. They shouldn't cause a restriction in range. So that's one problem with Pearson correlations. Now we're going to look at several situations here. And this just simply is you can follow through this on your own. It just shows you how we took the previous information and computed the correlation of 0.5 down here. Now let's say we have a situation where we generate two continuous variables that you could think of as U star. And we generate those variables so that the correlation between the U star variables, so the true correlation is 0.5. Now, if we can do a variety of dichotomizations of those variables. So let's say that here we have D55. That means that each variable has been dichotomized to be a 50-50 variable. And then so 50% in each category. And if we use the Pearson correlation and estimate Pearson, it's 0.33, whereas the true correlation is 0.5. If we dichotomize those two variables with a 90-10 split, then we actually get 0.25, so only half as large as the true correlation. When we go on to 3 categories, and you can see here we have a nice-looking distribution with 27%, 46%, and 27%, we get a 0.41. An even split into 3 categories also gets 0.41, and a more extreme split gets 0.39. Now, on the next several slides, we show a variety of situations. Actually, I'll just go over here. So I'll just tell you how to read the table, and then you can look at it later. So basically, Pearson correlation, the true correlation is 0.5. So then we've taken these U stars and we've dichotomized them in a variety of ways. A 10-90 split, 20-80 split, 30-70 split, 40-60 split, etc. 3 symmetric categories, 3 rectangular categories, and non-symmetric. Or negative skew, I'm sorry, and positive skew. And then anyway, the same thing down the columns, and at the very bottom, we have treating them as continuous. And then going over on this screen, it continues down. So you can then, if you look in the cells of the table, you see what the Pearson product movement correlation would be. So for example, for 3 symmetric correlated with a 10-90 split, you would get 0.26 correlation instead of 0.50. So, and I think the worst situation is when you have 2 negative skews, which, do you see where that is, Bengt?
1 negative and 1 positive.
1 negative and 1, I mean, which is it?
Dichotomous case, I think. Left there, 15.
Here.
Yeah, right.
Okay. So here we have an 80-20 split and a 10-90 split. So opposite.
1 row lower.
1 row lower. Okay. 90-10, 10-90. So you get a correlation here of only 0.10 when the true correlation is 0.50. Or you would get a tetrachoric correlation of 0.50. So this just gives you an idea of how attenuated the correlations are in different circumstances when you treat a categorical variable as a continuous variable. Now, what can you do when you have categorical outcomes? Well, if you have a lot of them, like let's say that you have seen that you have several categorical items, like 15 or more, that actually measure the same dimension. You've actually studied that. Well, rather than using the categorical data methodology, you could probably just sum those up and use them as a continuous observed variable in the analysis. That's one thing you can do. So if you're in a situation where you have a huge model and a huge number of items, that's one thing you can do. You can also create testlets. So if you have many, many items and you know they're measuring the same thing, you can sum up sets of them and use those testlets, those little summed up sets, as factor indicators in another model. So then they would be continuous, and you could get away from the categorical data methodology. And sometimes people estimate factor scores as in IRT and use those factor scores as variables in the analysis. Sample size, we don't give any recommendations, but in general it should be larger than you would have for continuous variables. And one thing that's very important, and that I see a lot, and you'll get this error message if you use WLSMV, is your univariate and bivariate tables should not have 0 cells. So if you have 2 binary items and they have a 2-by-2 table, you should not have 0 cells. And we'll warn you about this when you run WLSMV. We don't warn you about this in ML, although it's an issue. But if you do a type equals basic, we will warn you about that. So before you ever get to the position, though, of analyzing these categorical data, you should have looked at all of your univariate and bivariate tables. Usually when you have a 0 cell, it's when you have rare events, and it means that you just don't have a sufficiently large sample size for those particular variables. And I have to see what the next page is, too. Okay, so then after, these are references which I'm probably not all that familiar with. Do you want to
say a few
right?
words?
Do you want to say a few words? Why don't
Yeah.
you put it on that screen?
So here's actually an article about maximum likelihood item factor analysis with several items and several factors. Here is a good article in Psychological Methods again, which evaluates the potential sensitivity of the underlying normality assumption for the U stars. So the sensitivity to deviations from underlying normality of the U stars is studied in this article. And by and large, I think the findings are encouraging that small deviations from normality do not have very bad consequences. If you want to look at sample size discussions, my 1989 contribution to Bill Eaton in this building, or actually across, appeared in Sociological Methods and Research, where a bunch of methods researchers analyzed the same data, the ECA, epidemiological catchment area data having to do with depression, and that may be a useful article for you to take a look at. Here are two papers that talk about the effect of the skewness and censoring, floor and ceiling effects on assuming the variables are continuous when they should really be assumed to be categorical. And just a reminder, when Linda says Pearson product moment correlation, Pearson product moment correlation is the name we use for correlations for continuous variables. And if you apply the Pearson product moment correlation formula to two dichotomous variables, you get something that the psychometricians call phi coefficient, PHI. So the phi coefficient is a Pearson product moment correlation for two binary items for which perhaps a tetrachoric correlation would be better. So the phi underestimates the tetrachoric.
Okay, so now we're going to look at CFA with covariates, or the mimic model. And this is in the context of studying measurement invariance and population heterogeneity. So here Bengt has done this picture, and he's used the latent response variable formulation. So you have here, oh no, we were going to skip that. I forgot. Sorry. So we're going to be talking about CFA with covariates, mimic, in the context of measurement invariance and population heterogeneity. But given that everybody was here yesterday, and we went over this yesterday, the same concepts hold. So I think we just need to talk about what's different, actually, for categorical outcomes. And once again, on this screen, the same thing that we went over yesterday. We want to establish a CFA model, add covariates, and look at direct effects. So, and the issue being that a direct effect from a covariate to an outcome would indicate that that item is not invariant across the levels of the covariate. Now we're going to look at this antisocial behavior data. Once again, we've looked at that before, and we're going to look at 15 of the 17 antisocial behavior items once again. And they're dichotomous. We looked at this earlier, and this is the model. So we have three factors related to person, property, and drug offense. Property is F1, person is F2, and drug is F3. And we're regressing these on three background variables: gender, black, and age 94. So we'll just go through this rather quickly just to see what's different. So what's different here from looking at it as a continuous variable case is that we just have to identify the factor indicators or the outcomes as being categorical using the categorical option. And this is the situation where we're asking for the modification indices. We did that sort of as the third step yesterday with continuous outcomes. And we specified that all of the direct effects at 0 so we can get modification indices as shown in the output command. And we have our model results. Now, so the first factor and the factor loadings, nothing special really there other than the fact that these factor loadings are logistic regression coefficients, I think. Did we have ML? Whoops, he's gone. Let me look back. So this is weighted least squares estimation because we didn't specify maximum likelihood. So these are probit regression coefficients. So we have, and I'm just going to go through this because we don't need to spend time on this. And then we have the F2, same thing, probit regression coefficients, and F3. Now here we have regressed the factors on the covariates. So these direct effects between the factors and the covariates are looking at whether the factor intercepts are affected. So in the mimic model, remember, we can only look at factor means and intercepts, and in this case, the thresholds of the outcomes. So yesterday we looked at the intercepts of the outcomes because they were continuous. Today we look at the thresholds because they're categorical. But because the factors themselves are continuous, then the relationships, the direct relationships between the covariates and the factors are the same as they were yesterday. They look at a shift in the intercept of the factors over the covariates. We have, in weighted least squares, we have the old fit statistics like we had yesterday for continuous outcomes that we're used to looking at. The p-value is very, very small here. I think we have a very large sample size. And CFI and TLI look pretty good, although I think CFI could be a little bit better. RMSEA looks good when we don't really look at this very disappointing fit measure. But what we really wanted is to see our modification indices to give us an idea of which of the direct effects might be significant. So we can see the first column here isn't labeled, but it's the modification index. And we see the larger ones were for the direct effect for fighting regressed on age 94 and shoplift on sex. So these are very large. What the modification index means is that if you freed that parameter, chi-square would be reduced by that amount. We also have another very large modification index, con on black, 80.515. So now here's a picture, a path diagram where we've added the direct effects. So we have the direct effect from black to con, from sex to shoplift, and from age 94 to fight. So we've added this to the model. We've added it to the model command. So we've added these 3 on statements to the model command. And then we look once again at the fit statistics, which have improved slightly if you look at CFI and TLI by adding those direct effects. So this is just the same as what we did yesterday. So now we have our on statements. The 3 direct effects are listed here. And we can talk about how and you can go back and go over this because we need to make a certain amount of progress here. But the interpretation of the direct effect is in terms of probability, if you see here. So the direct effect is negative. For a given factor value, males have a lower probability of shoplifting than females. So, and that would not be expected. But we're not talking about a lower value anymore. We're talking about a lower probability. So that's the only difference. We're looking at thresholds instead of intercepts, and we're talking about measurement invariance in terms of not values on the variable, but the probability of a particular behavior. So this follows, but I want to go, and we're going to go on. These are just calculating item probabilities, which are put out in a lot of detail. I'm going to skip that, banked, and go on to multiple group analysis. So once again, we know the steps, fit the model separately in each group. First of all then, and there's a little variation here, fit the model in all groups, allowing all the parameters to be free except factor means, which are fixed to 0 in all groups, and scale factors, which are fixed to 1 in all groups. So this is something new. I mentioned scale factors with weighted least square estimation. You need to have scale factors included. And I hesitate to say this, but I have to. For maximum likelihood, this is slightly different, and for the theta parameterization, it's slightly different. And there's a section on testing for measurement invariance in Chapter 13, and it goes through all of the various models. So here is for weighted least squares estimation and the delta parameterization. So we only have 2 models to compare when we have categorical outcomes. That's one difference. So the first one is everything free, which would be factor loadings free and thresholds free, except factor means fixed to 0 in all groups and scale factors fixed to 1 in all groups. And a scale factor is 1 over the standard deviation of U star, the latent response variable. So then the second model for testing measurement invariance for categorical outcomes is holding factor loadings and thresholds equal across groups with factor means fixed to 0 in the first group and free in the other groups, and scale factors fixed to 1 in the first group and free in the other groups. And it doesn't have to be the first group. It just has to be one group. So we're going to look at the 2 inputs. So this is the one where everything's free. So you see the 3 factors up here in the model command. You see the factor means are fixed at 0. And then in the squiggly brackets, you see the scale factors are fixed at 1. When we mention in model mail in the group-specific model command the 3 factors and all of their factor indicators except the first one, then we're freeing those factor loadings. When we mention property $1 dash good $1 in square brackets, we're freeing the thresholds also. So this is what the measurement non-invariance model looks like. And here's what the measurement invariance model looks like. It's just the default model in Mplus. And then here's what the partial measurement invariance model looks like. So we are in model mail. We're freeing the factor loading for F1 by con and less than 50. We're freeing the factor loading for F2 by fight. We're freeing the factor loading for F3 by sold pot, and sold drugs. And when we free those factor loadings, we also have to free the intercepts related to them. So con $1 for con, less than $50 $1, less than 50, et cetera. And when we free the factor loading and we free the thresholds, we have to fix the scale factor related to that item. So down here in squiggly brackets, con at 1, less than 50 at 1, et cetera. And I think we should take questions. So basically, though, the mimic and the multiple group testing of measurement invariance are very similar. And they certainly share the same principles between continuous and categorical variables. They just differ in the details. And I think there's enough there for you to catch on.
And here you have the IRT diff plot. So with the same factor value, males and female differ in their tendency to shoplift. And again, remember that that's a conditional statement. Given the same factor value, probabilities are different. Question in the middle there.
Can you repeat or describe when you use IRT versus EFA for categorical variables and how it's different from latent class analysis?
So when you would...
So I think the question was when you use IRT and when you use EFA, exploratory factor analysis for categorical items. Do you want to take the first step?
I would say the same steps would apply as with continuous variables that we talked about yesterday. you probably, if you have a new set of items that you want to look at that are categorical versus continuous like we talked about yesterday, you would probably want to do an EFA where you place no restrictions and you just want to see how many factors there are. And then you might want to do a CFA after that, an IRT being a CFA. So the same kinds of steps as we talked about.
So before you get into unidimensional IRT, you want to make sure that you only have one dimension between behind the item set. Viewpoint.
Bruce?
For that practical issues section that you were talking about,
right.
You said that when you have categorical variables with sparse cells, or not structural zeros, but sparse cells, what that might mean for that, or even ordinal items that stack that went in without very many in the upper categories, is you got too small to sample. So it'd be great if we could go get more data, but if you can't get more data, you're stuck with the sample you've got. I guess the question is, what's the practical sort of solution to dealing with either bad distributions or dichotomies or highly skewed ordinal items when you're working with a fixed sample size and you're trying to figure out how to do your estimation?
Well, the problem is going to be when you have, the real problem I think is when you have zero cell. Sparse cells I don't think is as much of a problem. Is that correct? Would you agree? Okay. Yes. But when you have the zero cell problem, what it really implies is that the two variables correlate 1. That's the implication. And when two variables correlate 1, they don't bring any new information, so only one of them should be used. So
okay, let me modify that though. You could actually, from two dichotomous variables, where one cell is 0, you can create sort of a trichotomous variable.
But that's not always the case, right?
That's not always the case.
Yeah, there are certain times, in fact, we say it in the Mplus output. We say, think about combining these variables. So sometimes they can be combined, but sometimes it's not, the zero cell isn't in a place that makes sense to combine them. And then in that case, I don't think you really should use both of them.
And
but
here's a methodological distinction. Compare, in cases where you have 0 cells, compare the performance of using these U-star correlations, like tetrachorics, with using maximum likelihood estimation. Which is best? I don't think that has been done thoroughly. But the practical implication is to try to combine variables to avoid the 0 cells, I would say.
Sure, back there. You.
I have 2 questions. The first is, in what situations would you treat a continuous variable as a dichotomous variable if there's a very strong, for example, floor or ceiling effect? Like, how would you decide that?
So the question is when you would dichotomize the continuous variable? Is that the question?
Yes.
Yeah, so we don't want to give general rules of thumb, 20%, but we want to give you general guidelines. Censoring at 0 at 20% could be the rule. If you want to treat a continuous variable as a variable that has a problem, my own rule of thumb is if you have at least 20% in the floor or the ceiling, you may want to do something different about it.
But would
That's
you
a very rough rule of thumb.
But you're not going to dichotomize it.
I wouldn't dichotomize it necessarily.
No, he's asking about dichotomizing. And I mean, my bias would be that you lose information. You went to all the trouble to collect that variable as a continuous variable, and then you're just going to dichotomize it. You lose a lot of information. And if a non-normality robust estimator would work for that, which it should in most cases, don't you think, Bengt?
Well, when you get into a high degree of censoring for a continuous variable, the normality robust, as you said with these 2 pictures, the one on the right, that situation you would not want to treat as continuous variable.
No, but he's talking about a continuous variable and dichotomizing it.
Yeah, well, that was pretty continuous. It was 5 scale points.
We have our differences on this.
And that's good.
But anyway, so the answer to your question is, it sort of depends on the situation, depends on what the distribution looks like. And I don't think you can give an answer, and I don't think 20% is enough.
So there, wise men can differ. So look at the papers by Mutien and Kaplan that you saw in the previous couple of screens. We went through a lot of different situations to see how much piling up at 0 or at the floor and the ceiling would hurt you enough to want to work with categorical variable methodology. And again, you don't have to dichotomize like Linda says. You can trichotomize.
Okay. You had a second question.
It's more generic.
Okay.
It's okay. It's about missing data. I had the impression that you could actually, in Mplus, handle missing data in covariates. Is that true?
Well, the model's estimated conditioned on the covariates. And so the covariates are not part of the model. Their means variances and covariances are not parameters in the model. Now, having said that, and anybody with missing on 1 or more covariates is deleted, you can bring the covariates into the model by mentioning their means variances and covariances. They'll be treated as dependent variables. Distributional assumptions will be made about them just like every other dependent variable, but those cases won't be thrown out of the analysis. That's a mechanical issue. I'm not sure it's a good idea, and I'll let you go further.
Yeah, so it's true that the benefit of a model with covariates is that you don't have to make assumptions about the covariates, their distribution. All of these models are based on that idea. But of course, you can make assumptions about the covariates. You can assume multivariate normality, as is often done when you do so-called multiple imputation techniques, creating several different artificial data sets, which, by the way, Mplus can receive and analyze and summarize results from analysis of several imputed data sets. So you can bring them into the model, in which case we will treat them as multivariate normal. But we don't know how good that, if you want to do that for all covariates, for instance, binary covariates. And when you do multiple imputation, there are special programs that take into account the categorical nature of the variables by a so-called log linear location model approach, as in Joe Schaefer's program. So in some cases, I think it's okay to bring them into the model, but you have to be aware that you make an extra assumption beyond the model for be able to handle the missing data. Lady in the back.
Slide 108.
Slide 108.
How do you feel about the set of items in the screening tool?
Can you say that a little louder?
Screening tool.
Items used as a screening tool? Well, that's a good question to follow on the missing data area. So if I may extract free associate from your question, you have maybe a measurement instrument that is administered at time 1 for a group of individuals. And if you have a particularly high value on that screen, you get selected for further study. Is that close to what you're asking?
Behavior modification program or...
Right. So that's a missing data situation. If you have certain values on that set of items, you get selected, otherwise you don't. That sort of missing data is very controlled, and it is falling under the assumption of MAR, missing at random, which means missing very selectively. There's a long story about that in topic 4. But it is, if you work with the Mplus default, which is type equals missing, which you don't have to say anymore, and give the missing data indicator a symbol for the people who did not get past the screen, then you will do a correct analysis and be able to draw inference back to the original full group of individuals who were screened.
Is this a good set of items that you could use as a screening tool, even though it may not be a generally good measurement tool?
Oh, so you're talking about the quality of these items for a screening as a screening device? No, I think I would want to have a wider spread in these item characteristic curves. unless you're really caring a lot about if persons are here or here, you know. Could be a very narrow range. So this will tell you, yes, give you some information about whether or not that is a good screening tool. Yes. You pick the next one, please.
I'm sorry, what?
Could you pick the next person?
Oh, how about right here?
Some of your models you've identified by fixing the variance rather than an indicator. Is that compatible with treating that latent variable as an endogenous in a larger model?
So are you asking whether it depends on whether a factor is exogenous or endogenous, how you set the metric of the factor?
Right.
I don't think so, but I think I've heard that said before, so maybe you should comment.
No, I think you have the freedom to set the metric either in lambda or in the factor variance, be the factor exogenous or endogenous. You have full freedom. Yeah. You can do what you want.
How about right here?
Yes, if we can see slide number 155.
155?
We added 3 cases, right? Python 894 Shibboleth stack. I'm wondering that, you know, it's just right above. Python stack is also values like 60 point something, right?
Well, that's
right.
nothing. 60 is nothing.
No.
So what if this one more path is like Python stacks? I'm just
Okay.
curious about, you know, it's
Well, one comment that, is that okay if I
Yep,
comment on it? Okay, but basically, each one of these numbers only holds for one parameter being freed. And then we would really have to rerun the analysis to see what these other numbers looked like. So, you know, if we free this and we rerun the analysis, this might not be 64 anymore. It might be much smaller, and this might be smaller. So, you know, when you look at the modification indices, although we're choosing 3, we should really probably choose 1, see what happens, and see the next set of modification indices, and then see what's the biggest one there, and then run it again. You know, would you?
Yeah, exactly.
Okay.
Can I just ask one more question?
Sure.
If we can see the next page, 157. Yeah, could you recommend what kind of software that we might use to make that kind of?
Well, what we use is freehand.
Aldus freehand.
Aldus freehand.
Aldus freehand.
It used to be called that.
ALDUS.
ALDUS.
ALDUS. Freehand.
All right, and people who come to work for us and they come up to speed very quickly. So it seems to be a pretty easy program. I don't know how to use it, but.
I could never do it, but it's easy.
Well, yes. 153?
Slide 153, folks.
Standard error that's all going through there. Just these covariates are going to be the relevant ones to look at in the modification indices. Is that all?
Well, or in here, this is from the mimic model, right? These could be important covariates to use. When you look at the modification indices, they might suggest covariates to use, or rather grouping variables to use in a multiple group analysis. But in this situation, 3 of the covariates, we added direct effects for 3 different covariates. So that doesn't give you a great suggestion. So many groups.
The gentleman in the far left back there.
Yeah, on slide 130.
130.
Yeah. When you were talking about when to treat variables as continuous and categorical, the first bullet point about the number of categories versus floor and ceiling effects. If, say, you were in the situation of having to defend to a reviewer the choice of continuous versus categorical, is there a literature you can refer to that makes that point?
Is there a literature on this? Well, there is that, the 2 papers by Mutin and Kaplan in British Journal of Mathematical and Statistical Psychology. I'm sure there are many other sources. Can't think of them though, but you know, you're always fine if you treat it as categorical. But of course, when you treat it as categorical, you get yourself into working a little bit harder and the computer working a little bit harder. So sometimes you want to make it easier and treat them as continuous. But I think you can refer to that.
Okay, in the middle back? Yes?
Yeah.
Okay. Slide 109.
109.
The test information as the precision with which these factor scores are estimated.
Yeah.
How can I use this factor score? Can I use it somehow to select the items?
Can you use the factor score to select the items?
So
yeah, you use this function. The look of this is used to select items. That is, if this has too narrow of a peak, which this looks like it has a narrow peak, although you would want to know the standard deviation of f here. But if it has too narrow of a peak for your taste, you would choose some items that are less extreme and some items that are more extreme as measured by the these item characteristic curves. So you would try to write more items or change item wording so that these are spread out more to have a wider peak. Now, I'm not an educational item analyst expert, but what does Iowa City say? She left.
Oh, she left.
That, you know, voting with your feet.
You're right. But I think if that's fine.
We have a comment.
This is an event. It only happens one place. So when you're talking about easier crime items, it's not that standard.
Well, less bad crimes.
Yeah, less bad crimes, less serious crimes.
Like lying, white lie.
Yeah. Yeah, white-collar crimes, right?
Well, those are pretty serious. Take a look at our retirement account.
Over here is murder, yeah. Okay.
Exactly. Yes.
Yes.
And all of those are clustered in the middle is leading to that peak.
Makes sense.
Exactly, yes.
So when those are spread out, that spreads out.
Now you're taking the whole IRT course.
There's nothing left. Yes, quick question here.
That peak also depends upon the discrimination values.
Yes, exactly. Not only on the shift sideways, which has to do with the threshold or difficulty, but also the steepness, the discrimination, the slope. Yes, absolutely.
While we're on this page, does Mplus also generate item information functions?
Yes. In the plot.
In the plot command.
Plot part of the program, yes.
Over here.
Is discrete time survival analysis a special case of IRT?
I didn't hear your preamble.
The discrete time survival analysis?
Oh, discrete time survival analysis. Does that have to do with IRT, is what you're asking?
Yeah. Is it a special condition of IRT? Because when I read the slide 98, the model setup is very similar as the discrete time survival analysis. That F by U1 to U5, F1, and the...
Now you ruined the whole surprise for day 3 or 4.
No.
So, just to repeat the question, is the setup for discrete time survival analysis similar to the setup for IRT? Yes, in the sense that in both cases you work with dichotomous items, and you can work with a factor in both cases. But no, you score the items differently in discrete time survival. You have event history indicators. So it's longitudinal. You go from early to late, and you have 0, 0, 0, the event hasn't happened, then 1, the event has happened, and then 9, 9, 9 missing after it's happened. So that's a little bit different scoring of the items. But there are some similarities. Yeah.
Yes.
When might you use unweighted least squares instead of weighted least squares if you're doing factor analysis on categorical items?
EFA or CFA or?
EFA.
Yeah.
I think unweighted least squares is pretty good for EFA. Unweighted least squares says that you give equal weight to every correlation. And some correlations have more sampling variability than others, and maybe they shouldn't be given equal weight in estimating parameters, and that's what weighted least squares takes into account. But in EFA, you only deal with the correlations, so maybe equal weight is okay. But when you do CFA, particularly when you do multiple group CFA, you also bring in means, thresholds, and things like that. So thresholds and correlations are on different scales, so you may want to, with different sampling variabilities, so you may want to weight them. But in standard EFA, I would say ULS, unweighted least squares, is just fine.
Follow-on question?
Sure.
What about sample size in relation to those two estimation techniques? Sort of, I remember, and it's been a while, I didn't understand all of it, but from your paper that you've been referring to about ordinal items, what kind of sample size do you need to be able to use those methods? I think your lower limit was around 200 for the estimate for the Monte Carlo studies you were running. So, what, 200 would be great, but I'm working with data. Sometimes it's only 100, 150 observations.
Right. I think if you fall below, as you say, 200 is a good requirement for this default estimator, which we call WSMV, to work well. But if you fall below that, I would probably switch to unweighted least squares and probably only focus on the point estimates, not the standard error or chi-square Tesla model fit. So, the point estimates are okay at lower sample sizes than the standard errors. More questions? I think we need to have a break.
Yeah, so let's have a 15-minute break.
15 minutes, but be back here because we're going to start, and we're going to talk ESEM, and you might miss it. All right, folks. We have just about another hour together before we have to, yeah, I know. We have to say a tear-filled goodbye and see you in March, perhaps, for the continuation of the saga. We do not offer any training sessions on Mplus between now and then, having given them 4 days last month and 2 days this month. We'll take a little break and focus on the development of version 6 instead. Now, next year, we will announce on our website when the March session takes place very shortly. Actually, Monday morning, you will see a whole new set of postings on our website. Quite a few new, I think 10 papers are being posted and other information. Updated handouts from these training sessions. And soon enough, we'll get the dates for March. And after that, we'll probably get the date and location for a European excursion next summer. And onwards and upwards. And then back here in August again. So we have time, folks, to talk about a topic that I think is very exciting and doesn't exist anywhere else. These facilities are totally unique to Mplus, and that is what's been termed exploratory structural equation modeling. It sounds like an oxymoron, but I think it's a very good, useful approach. And a lot of credit for this development goes to our Mplus colleague, our statistical programmer, Tiomer Asparojo. He and I were dreaming together, and he, with his skillful algorithmic programming skills, managed to implement it, which in the general program setting, which is no small feat. So what I'm going to do here in the last hour to give you a brief overview of EFA as it connects to CFA and as it connects to SEM. And I'm going to go back and focus on continuous outcomes for simplicity, although everything that I say can be done for categorical outcomes and censored outcomes and the combinations of those kinds of outcomes. So what we're offering here, it says it's a new approach to structural equation modeling, but it could just as well have said, and should have said in addition, that it's also a new approach to EFA. More general EFA approach. So I'm going to give you some examples at the end and point you to other places where you can find more examples. So let's talk through this story. The history is that EFA used to be the only technique for factor analysis, and it certainly is if not the most, one of the very most frequently used multivariate analysis techniques. It has, however, well, let me first say that 1966 was a good year, but where Bob Jenrick at UCLA solved a significant rotation problem by deriving a direct core-to-mean rotation, a oblique rotation, that is correlated factors representation. Before that, the rotations were not always placed on a sound algorithmic base, but he's a very skillful numerical analysis-oriented statistician who accomplished this. And as I said, for a while, core-to-mean was our default, but we have agreed that a new rotation geomin is even better. Jenrick was also the first to develop standard errors for rotated solutions, although most programs don't have that implemented yet. And we tried to make arguments referring to Kudek and Odell's article in Psych Bulletin for the virtues of working with standard errors for rotated solutions. Now, perhaps why this hasn't made their way into standard statistical software to a large extent is because of the 1969 psychometric article by Joris Skog, who developed confirmatory factor analysis, where there are no rotations, and where in line with regular maximum likelihood estimation, standard errors is an easy byproduct of the maximum likelihood estimation through the so-called estimated information matrix. Whereas it's not easy to develop standard errors for rotated solutions. Joris Skog developed CFA further into structural equation modeling in Lisserl, where CFA was used for the measurement part of the model. So CFA for the measurement part of the model. And unfortunately, we have sort of accepted that if we want to do structural equation modeling, we have to work in a CFA context. And that's not at all true. You can stay with EFA and be working with structural equation modeling. Likewise, people thought that CFA was necessary when you wanted to do multiple group analysis. When you wanted to do multiple group analysis, say comparing males and females, you couldn't work with EFA. You had to switch to CFA, which is another fallacy. And I'll give you an example of that. Structural equation model looks like this in its full glory, the measurement model and the structural model. And in SEM, we typically specify the loading matrix here in the measurement model as having a simple structure. Simple structure meaning typically that a variable loads on only one factor, only one latent variable. So all of the items, any one item is influenced by only one factor. So it looks like this in the loading matrix, x meaning a free parameter, and then zeros. This is a simple structure. But that really places a big burden on applications, I think, because very often we are not able to develop measures that are so pure as to follow this simple structure. Those zeros are not necessarily exactly zero. Even if you have a theory of two factors, it's very hard to come up with items that measure in this exact simple structure with exact zeros. And if the truth is not an exact zero, if you have what Linda called a cross-loading here or here, and you impose this simple structure, you will distort the results. Here's an important quote from Michael Brown, who has written a very good overview article on rotations, and we pointed to that before, in multivariate behavior research, writing about rotations in exploratory factor analysis. So take 30 seconds and enjoy that quote, folks. It's a thoughtful quote. So often, researchers have theories and have been encouraged, I think, overly encouraged, to go straight from theory to CFA. And then they will inevitably find that their CFA model is rejected. and they will try to modify it desperately to get their paper published. And they love the modification indices, but the procedure then becomes exploratory. And in that situation, the use of exploratory factor analysis is preferable, is what this very prominent psychometrician argues, and I would agree with it. So we think there's been an overemphasis on rushing to CFA. And you see it on SEMnet as well, that people say, if you have a theory, don't use EFA, use CFA. But you know, your theory may only be as strong as to say, I have M factors, and I think that these measures will load more prominently on certain factors, but I don't really know if they're going to load exactly 0 on the other factors. That's a perfectly good hypothesis that you can have. So that's an argument that you can have a EFA measurement structure. You don't have to have a CFA measurement structure. So if you take that tack, what does that lead you to? It leads you to this new approach, where in your SEM, anywhere you want to, where you have the multiple indicators, you can allow an EFA measurement model part integrated with CFA measurement parts. So part of the model can be CFA-ish in its measurement. Some parts can be EFA-ish. And this will allow you to do EFA with correlated residuals. It will allow you to do EFA with regressions on covariates, like mimic EFA. For instance, when I analyze these antisocial behavior items, I often try to impose an M-squared restrictions only, an EFA within CFA structure. And I did that for years, having to set it up painfully. Now we have it much more automated, where the program automatically rotates, and as we will see, it rotates not only the loadings, but it rotates the structural coefficients as well accordingly for the regressions of the factors on the covariate. And regressions between factors on different EFA sets can be handled, plus regressions between factors of EFA and CFA measurement sets, plus multiple groups. And I think this is a very powerful addition, that you could do multiple group EFA. I think that would become very popular if I dare to predict. So you can study gender invariance while staying in an EFA setting without having to go to the CFA setting. And you can impose EFA loading matrix equalities across groups or across time, time being the longitudinal factor analysis, like test-retest situations. And you can impose mean structures. It doesn't have to be only correlation structures or covariance structures, but mean structures, which you will find in, say, growth models that we're going to talk about in March. And all of this is available for the combinations of these kinds of variable types. Not yet for counts, but for continuous, categorical, and censored outcomes. Now, just technically speaking, factor indeterminacy and rotations are still an issue because we have to do with EFA. And I'm going to skip this slide because we've already talked about rotations. And I'm going to go to the next slide instead. Noting that when you get into exploratory SEM, the choice of rotational scheme, rotational method is important because you're no longer relying on CFA, no longer relying on a specific substantively motivated fixing of zeros, which may be too strict. And therefore, both Michael Brown and Tiermaras Barojo and I have studied the different rotational schemes and found that geomin is the winner. So particularly with variable complexity greater than 1, that is a variable loads on more than one factor, so-called cross-loadings, geomin, generally speaking, is better than conventional methods such as Varimax, Promax, and Quartermin. If you have more information, more substantive theory, you can also consider target rotation, where you say that I know that there should be certain zeros, zero lambdas, zero loadings, but I don't want to specify as many as EFA says I should specify. then you get into the so-called target rotation situation. It's sort of halfway between EFA and CFA. And it's also described in the Michael Brown article. Target rotation between mechanical rotation, which is the EFA rotation by rotational algorithms, at CFA. So it's rotation partly guided by your judgment about the substantive theory. So you choose your target loading values, and they're not fixed as in CFA, but they're just targets. 0 targets can come out big if misspecified. And without getting into the details, they're described here and in Brown 2001. Mplus language is very simple. A target is Y1 being indicated for F1. If you have the target of this being a small loading, you say this little curl Y1 not at or not asterisk, but curl 0. And I'll get to the language over there on the right later on. But it has to do with the ESEM situation. And as I said, I'm not going to go through this page, but you know, we have the rotation of lambda is expressed here, but that also implies a rotation on the regression of eta on x's. So you see that gamma is also rotated, and so is beta, the matrix for relationships between etas. So the rotation, you know, when the factors rotate, factor loadings matrix gets rotated, the factors change meaning, and therefore the structural relationship will change in their coefficients. And that's the strength of this approach, that you can rotate all of that. Here's another technical slide, which is not suitable for a quick go-through today. Suffice it to say that it's technically quite complicated to accomplish this. And we have a long article in the first article in this latest issue of the SEM journal, as I mentioned before. What I'm going to do is I'm going to take some time and talk through an example instead, so you get a feeling for the power of this. And other examples are given as web talks that you will find on the Mplus website. And those web talks correspond more directly to the article in the SEM journals. So we're going to talk about a mimic analysis with cross-loadings in one web talk, and a setup for longitudinal EFA test-retest EFA in another web talk. But I'm going to give you a new application, multiple group EFA, which I actually have saved or intended to work on more for a psych methods article, but who knows if I get time to do that. But in any case, it's sort of an interesting situation. So let me actually put it over here. So we have an example. Here is, since we are in Baltimore, we're borrowing Baltimore data from Nick Ailongo, his cohort 3 study of students in Baltimore public schools. And it is, in this case, cohort 3, the third time around that he followed students from first to up to 7th grade, I guess is how far he follows them. And here you have students in 3rd grade, and we have 261, 241, 48 males and females. And the outcome is teacher-rated aggressive disruptive behavior in the classroom. And the outcomes are on a multi-category scale. It's non-normal, but we're going to treat them as continuous variables, but taking the non-normality into account by using the MLR estimator. So non-normality, robust standard errors, and test of model fit are going to be provided. And I'm going to, although we could have treated the outcomes as categorical as well, we could have carried through this ESEM approach. 2 types of analysis. One is we're going to do a standard EFA in each group separately using GeoMin, and we're going to discuss the difficulties of interpreting that. So the gender-specific analysis, the difficulties of comparing. And we're going to do a multiple group EFA analysis of males and females jointly. So since I say multiple group EFA, I am referring to a special case of ESEM. So this is only possible through ESEM. So I'm going to talk about the example first and then give you setups for this in Mplus. Before that, we need to talk about some technicalities before getting into the substantive story, and I'll show the same slide on both screens. EFA, ESEM, analyzes a sample covariance matrix, not sample correlation matrix. It's always safest to work with a covariance matrix, not to lose scale information, particularly in this case where you may have models that are not scale-free, so to speak. This means that the unstandardized solutions are going to give loadings in the original scale of the indicators. So if you have a variable on the high scale, the loadings are going to be big. But you can request a standardized solution which gives the loadings in a regular EFA metric. If you remember EFA, the loadings are presented automatically in a standardized solution fashion because we fix the factor variances to 1 and we analyze the correlation matrix, which implies that the indicator variances are also 1. So the independent and dependent variable variances are 1. Therefore, the loadings are presented in a standardized fashion already. That's why you don't see a distinction between standardized and unstandardized in regular EFA. So to give you the solution in a regular fashion, you can request a standardized solution. Now, multiple group EFA allows variances for the factors, variances, covariances for the factors to differ across groups as a default. Just like in the multiple group CFA that we talked about yesterday afternoon. We want to study that population heterogeneity. When we have measurement invariance, it makes sense to look at the group differences in the factor variances and covariances. And because of that, we will work as follows. Group 1, standardizing to unit variances. So group 1 works with a factor correlation matrix or presents a factor correlation matrix as the result, while other groups present results in factor covariance matrices. So group 1 will be the reference with factor variances 1 to which we compare the factor variances for the other groups. So that means that if we have an assumption, a model specified as having group invariant loadings, measurement invariance with respect to the loadings, it will still give group varying standardized loadings due to group varying indicator variances and group varying factor variances. Group invariant loading says that the unstandardized loadings are equal across groups, right? Unstandardized loadings are held equal across groups. But when you standardize, as we said up here, you will get unequal loadings across the different groups. That's just telling you what you should expect. All right, so now we're ready for the action, and here it is. You can look at it with a red heading or a black heading. So I'll stay over here. So here we've done two analyses, one for males and one for females, of the variables. Aggressive, disruptive behavior in the classroom. The student is stubborn, breaks rules, harms others on property, breaks things, yells at others. Sounds like a regular classroom, right? Very active little children. And we look at the boys, and we look at the girls. This is in 3rd grade. And it looks like, if you do separate EFAs, that 3 factors is pretty reasonable. If you look at loadings for the males, and they are in a standardized fashion, if you do a regular EFA, that becomes the automatic output. You have a verbal, aggressive, disruptive behavior, lies, fights with classmates, and where is it? talks back to adults should be highlighted there as well. Talks back to adults. And what else do we have? Loses temper. What's that? Stubborn. Also, stubborn should be bolded. Yes, so lots of boldings have slipped away here. Stubborn and bold talks back to adults and loses temper. So, yells at others. All right, you can find them. You're a quick factor analyst now. Now, do you use the rule of at least twice as big as anything else in the same row? Works pretty well. So we have verbal aggressive disruptive behavior, and we have person-oriented aggressive disruptive behavior. Harms others. Here's a bad item, by the way. Harms others and property. Is that personal or is that property behavior? Well, in this case, it's interpreted as personal offense. And here, is this bolding right? It looks like the bolding is off here. You should bold fight here. Yeah. Yeah. So we bold fight here, and you also bold. Well, now I remember the story better, folks. Why don't you do this? Why don't you underline the big item loadings here? 0.82, underline 0.66, 0.61, and 0.64. And for person, we underline harms others and property, fights with classmates, maybe teases classmates. And for property, we underline harms others and property, break things, takes others' property, and nothing else. Say that again? Harms property, yeah. Harms property, let's underline that as well. So now you can tell this is newly created slides, fresh for your enjoyment. Underlined items are the items that represent each of the factors well. The bolding, however, is what distinguishes males and females. So now I know how to present this next time. It won't be a next time. Look. Oh, this is just the first last tour. Now, if you look at females, so that makes a lot of sense for males, right? The males' loadings make a lot of sense. Now, if you look at females, the females differ from males' loadings in the instances of the bolded lines. That was why the bolding was done. So look at harms others and property. In that female EFA, it turns out you have a highest loading for verbal, whereas males have it for person and property. Females have it a little bit for property, but if anything, they have it on verbal, not on person. And look at takes others' property. Males had the biggest loading on property. Females has it on person. So it jumps. And I don't know why takes other property is person. Well, I guess you have to approach that person before you can take it, but it seems like it should be a property loading item. The male solution makes more sense. Lying, females, for males, lying loaded on the verbal factor. For females, it loads it more on the person factor. And for fighting with classmates, males said that that was a personal offense. Females say that that is a verbal offense. So for some reason, maybe we have an unsuccessful rotation here for females, whereas for males it makes a lot of sense. And we can ask the question, are these genders really different? Is the factor loading pattern really significantly different for males and females? And to make a long story short, the answer is no. There is no significant difference between males and females in the loading pattern, as we will see. But you couldn't conclude that from this outcome, right? Because you have made no effort to rotate them to the same target. No effort to rotate them to the same target. So what should we do? And you see that the correlations for the factors then are quite different. because the factors are not measured the same way for males and females. So the verbal property correlation is 0.32 for females by 0.56 for males, 0.22 here, 0.68 here. The factors are not one and the same. We can't compare. Here's where ESEM comes to the rescue. Aligning the loading matrices for the two genders, we will entertain three models, model 1, 2, and 3. Model 1 is our standard invariance model. Loadings and intercepts are invariant. Model 2, we have loadings but not intercepts invariance. And model 3, neither loadings nor intercepts invariance. And a priori, on the face of it, it looks like model 3 is the correct model, just looking at the separate EFAs. But in truth, as we will see, model 2 is the winner. So what we're looking at here is the log likelihood for our H0 model. And we have a non-normality scaling correction factor that we will use in this column that we will use for chi-square difference testing. Number of parameters, degrees of freedom, chi-square, CFI, and RMSEA. All of these models are acceptable from a CFI point of view, and at least model M2 is acceptable from an RMSEA point of view. We will make two comparisons here, and the interesting thing is that this ESEM EFA can make these comparisons. We can compare M2 and M1. M2 and M1 tests whether or not we need to let the intercepts be different. It tests whether or not intercept invariance it really holds. And the difference between M1 and M2 is the intercepts, right? So does the intercept invariance hold? Well, if you compare them, the way to compare these is to do a chi-square difference testing. And on the next slide, 191, we give a reference to the spot on our website where that kind of log likelihood difference testing with scaling corrections is carried out. It's described how to do it. And the way it's done is as shown above there. So if you go back to slide 190, this TRD is the chi-square value that you obtain. So TRD is the chi-square value, 98.5 with 10 degrees of freedom. That's testing M2 versus M1, which concludes this is significance. So not all intercepts are invariant. It says choose M2, model 2. If you then compare M3 with M2, that is, test whether the loadings are also not invariant. M3 says that the loadings are not invariant. Well, if you do that, you will get a chi-square that is pretty low relative to degrees of freedom, and we cannot reject that the loadings are invariant. So we find that the loadings are invariant when we choose M2, which you wouldn't have concluded from the separate EFAs. So what does it look like? When we use model M2, which is then a multiple group, a two-group simultaneous analysis of males and females, what does it look like? I'll show it on both screens. Well, it looks like this. And here you have presented the multiple group analysis in a standardized metric. So even though you impose equality of loading matrices, model M2 imposes equality of loading matrices for males and females, the standardized solutions will have different values. But the high and low values will be in the same spot. So now let us check the 4 instances of problematic items for which the loading patterns disagreed between the gender. Here, lined up pretty nicely, harms others and property, loads on person and property. You know, that ambiguous item. And it does so for females as well. We didn't see that before. Takes others' property, loads on property, and load some property for females as well. It does have a verbal component, but it does also for males. For lying, now females agree with the male analysis that lying is a verbal, aggressive, disruptive behavior. And for fighting with classmates, it's again a verbal and a person offense for both genders. So there you have the agreement. And statistically, you cannot reject that it is the same factor pattern. So I think that's a really useful technique for studying invariance across groups, which would be the first thing you would want to do once you've done EFA in one group. You want to see what's the measurement structure in other groups. And here is a disciplined way of approaching that problem that gives you statistical backing for, in this case, saying that the genders have the same factor pattern. So rotations are not always successful. You may be seeing differences. And you would never know if from separate EFAs, you would never know if the differences are statistically significant unless you force them to rotate to the same lambda and give a test of that being the same or not. So that's what we do here. So we hope that catches on, and you can learn more things from it. Factor correlations are then more aligned here. The values are more of the same magnitude. You have a little bit higher person-verbal correlation for females, but you don't have as big differences as you saw before because you didn't measure the same factors before. Here you have the variances, and you do a multiple group EFA. Males are standardized to have unit variances, and females are allowed to have different variances, and they turn out to be larger. So there's more heterogeneity for females on all of these factors, and perhaps in particular for the property and the person factor, females vary more than the males do. So you can learn something about factor variance differences across groups and factor correlation differences across groups while being certain that you have loading matrix invariance. We didn't have intercept invariance, measurement intercept invariance, which means across groups, which means that you couldn't compare mean structures of the factors across groups because you're not having that intercept invariance, which is a useful finding as well. Input for model 1 and 2 in Mplus, very simple. I predict that you will fall in love with this. Model M1, that was total invariance. Total invariance across groups is our default, so it comes out particularly simple. You say that so this is EFA and ESEM. You say that factor 1 to 3 is measured by all of the items. And Mplus will figure out which factor influences which item. So you just rattle off all of the use variable items and say that you have three factors. And to designate that you have ESEM, you have a parenthesis asterisk, and then you give a label, any kind of label, like you can say parenthesis asterisk ESEM. I'll just say 1 there for simplicity. So you have a multiple group analysis. You see that line up here, multiple group analysis. And all of the variables are mentioned here because you're doing an ESEM EFA for all of the variables. You're only specifying that you have 3 factors. Model M2 on the right screen, there we have only loading invariance. So the by statement is not repeated for the males, but we let the intercepts be male group specific, in which case we have to fix the factor means to 0 for identification. But you still have the ESEM specification, parenthesis, asterisk, and a label. And then model 3, where nothing is invariant. Let's see, this is model 2, model 3, nothing invariant. You repeat the by statement in the model male group So you have a group-specific factor loading matrix here, as well as a group-specific intercept arrangement. So it's quite easy. Further readings on this is in the latest issue of the SEM. So this 2008 paper is now published. And the second article in that special issue is an application by Herb Marsh, who is one of those who's fallen in love with this technique, pointing out that very often using the ESEM approach, you will get much more distinct factors, much more uncorrelated factors than if you use CFA. Maybe you can close the door, if you don't mind. And this then makes it possible to argue for distinct factors using the ESM approach. That is, that you have a discriminant validity, whereas in the CFA, when you force the strict cross-loadings at 0, you force the correlations between the items to go through the factors. So you inflate the factor correlations when you fix 0 cross-loadings that shouldn't be there. All of this is described in more detail in a web talk that's been recorded, sits here. And it's not described in the current user's guide, the book, or what's on the website. But on the website, you have a version 5.1 language, an example addendum, which covers ESEM. So if you look at the language and examples addendum, you get several, I think 6 different examples of how to do this beyond the examples you have here. We're going to skip this last section, technical issues for weighted least squares estimation. Give you a relief of that. And instead, stop here and invite questions and answers. And since some of you will be heading out, and we'll be heading out shortly, Linda and I just want to take this opportunity to thank you for being such a nice, enthusiastic audience. It's a pleasure to interact with you, so thank you. So let's see. As I take the questions and the answers, Linda will pack things up here, she says, and we'll be heading out.
And don't forget to leave your badges on the table back there.
All right, here's mine. All right, folks, so let's see who has any to ask a question. Yes, gentleman over here.
Yeah. In terms of the usage of ESEM for EFA, I'm wondering, what if have some basic data, it's like couple data, because I'm assuming that for this sample, this may be males and females are independent, right?
Yes, right.
If it's wives and husbands, those are interrelated. So I'm wondering if ESEM will work.
Oh, remind me of that, Linda. Do we have ESEM for type equals complex yet? Yeah. So one approach to that we talk about in the multi-level topics, 7 and 8, is to say that we have analysis type equals complex, which then has a cluster, the dyad, and the dyad member correlations be accounted for when you compute the standard errors and chi-square test of fit. So we believe that type equals complex is available together with ESEM. Yes. Yes?
Can you comment a little bit more on what you said about how
Right. So the question is about discriminant validity, and I refer to this article, the second article in this new issue of SEM. And Herb Marsh is interested in the analysis of the big 5, the 5 personality factors, and in factor analysis of student or teacher evaluation forms. And he finds in these empirical studies that taking the ESEM approach, by and large, gives you much smaller factor correlations, whereas the EFA approach, with its simple structure, cross loadings of 0, gets much higher factor correlations. And I brought in the term discriminant validity. If you have low factor correlations, the factors are more distinct. And that's all I meant by that, that the factors are more clearly different quantities when they have lower correlations. So if they correlate 0.3 instead of 0.7, they're more distinct. So that's what he discusses in his paper. More questions? Yes, Bruce.
I know that it's nice to have a loading that's twice as large as the closest loading for separation, but even in this example for Model 2, some of those items don't really make that cut. I was wondering whether or not they're, how close they can be before you decide that there isn't really good separation for an item.
So you're referring to this slide 192? Could you take an example that we could talk about?
Either takes others property or classmate for females.
So it takes others property, and you're saying that this loading is not twice as big as this.
Also, and certainly not for females.
Right, right. And what's your question again about that?
So how do you decide to assign an item for exploratory or even I mean, for this type of ESEM EFA or even regular EFA, when the loadings don't make the 2-to-1 cut?
Well, I think that is a problem if you want to turn this into a CFA. If you want to turn this into a CFA, you don't know if you should fix that one to 0. But for EFA, you can just let it be as it is. And all you're really interested in is whether or not this is significant.
Assigning the same item to more than one subscale.
True. True. In that case, this would not be a good item, and you may want to get rid of it. For some reason, people read, although you think it has, you wrote it to measure property violations. The person reading this, the teacher, thinks, okay, that means they're going to scream and dominate the person, thereby take, verbal approach, take the property. I don't know, but in that case, yes, you would want to throw it away. Yes? Correlated errors is a possibility, yes. And you just say y1 with y2, for instance. Yeah, it's that simple. And if you allow for correlated errors, you may find a different EFA structure, factor pattern, than if you had not allowed for it, which you don't do in EFA. So yeah, there's a greater flexibility in that case too. Yes, Mr. Yellow from Cincinnati.
Yeah. Okay. Slide 182.
Slide 182. The laser pointer is packed, but I'm the laser pointer.
Of these parameters seems to have gotten rotated. So how do I think about these new rotated betas and gammas?
Yeah, so the structural parameters are also rotated, yes. So when you rotate to get a simple loading structure, hopefully a very interpretable loading structure, the meaning of the factors change, and therefore their regression on covariates, say, will also change from gamma to gamma star, as it should be, yeah. So it is a multiplication of those estimates that takes place to get to the rotated structural coefficients.
More, so the original betas and gammas are more attenuated. Is that how do I think about the original?
Well, there is really no original gamma, because we are exploring, in a sense, we're exploring the factors. We're letting the rotation determine what the factors are. We're doing exploratory analysis, so there is no original gamma in the substantive sense. In the computer sense, there is a first starting value gamma that we then rotate, but that's more of a mechanical answer. Yes?
Is there any geometric solution for this? I know for example, one is for solving, the other one is on this geometric description of this relation.
Question is there a geometric description of this? Well, you know, some factor analysts love geometry. That was never my way of looking at factor analysis, so I couldn't say. But I'm sure this has beautiful geometry behind it. And you might be the person to bring that out. Okay, more questions? Maybe you want to catch your plane ride too, which is totally understandable, folks. So thank you, and see you back in March. And Linda, thank you.